How we doing, everybody? It's coffee time. Well, I got a copyright strike. No more copyright strikes. How we doing, everybody? Welcome to a beautiful Monday. Hope everybody's doing good out there. I'm doing fantastic. Thank you for asking. Let me just get everything started here. The fireworks are going crazy. I love it. All right. Get this up in here. All right. Alrighty, everybody. Just like the title says, today's finally. It took us almost a whole week to get through chapter 11. Well, we did a lot. We really hammered subnetting and everything else. So I feel pretty confident that I got subnetting down. I mean, I spent a lot, like I said, we spent all week pretty much subnetting and whatnot. And it was so funny. After all that, what was it, Saturday, I did like a quick lab before I went to work. And I don't know if it's because of lack of sleep or whatnot, but what was it? I ended up going back into it Sunday because I just couldn't. I was like scratching my head all after I did it because I biffed it all. I biffed it hardcore. So I created a lab on Saturday and in CML, and I was doing, I was trying to subnet it out to where the point-to-point links were only using, a subnet that only had only two IP addresses in it. You know what I'm saying? So I was trying to like reserve. I was trying to be like really conservative about how I was doing my subnetting plan. Well, what I did was, and this is what I ended up figuring out what I did afterwards, and it's so funny because it was like, so after I did everything, it was like I could not make adjacencies for the life of whatever I was thinking. I was scratching my head. Why isn't OSPF making adjacencies? Why isn't OSPF making adjacencies? And I'm like, did I mess up the wildcard address? And where did I go wrong? Did I mess up DHCP? And I just could not, like, I was totally stumped. And then obviously I had to rush off and jump off the stream and then run to work. And I was thinking about it that whole night. I'm like, what did I do wrong? What did I do wrong? I'm like, I've done this so many times, and now all of a sudden when I go to try to be conservative about my IP addressing, what did I do wrong? Well, I'll tell you what I did wrong. So while I was being conservative with those point-to-point links that I was creating, even with the it was mainly with the sub interfaces that I was creating for the VLANs to go to the other areas. So I had area 1 and area 2, and respectively each one of those were divided off of a switch to, one was off of VLAN 10, one was off of VLAN 20, and I had VLAN 1 as the native VLAN. The switch had no IP addresses. It was just acting as, just a switch with VLANs. But the router, the edge router, quote unquote edge router, it was a similar topology like I made in Packet Tracer. You know what I'm saying? Where I had the edge router, and the edge router was doing GHCP for the like the areas and whatnot. I was having the edge router do DHCP. I wanted DHCP to allocate addresses and gateways to the like the inside local routers. You know what I'm saying? At least on that one side interface. You know what I'm saying? The interface that was facing the like the inside, the outside, the inside outside area, the local outside. So I had, obviously on the area router, you have your local outside, and then you have your local inside. I was having DHCP allocate addresses and gateways to the local outside interface, and it was funny because DHCP worked fine. It allocated an address to that local outside, but then OSPF just wasn't making an adjacency to that local outside interface, because what I was doing next is after DHCP dynamically allocated that address to the local outside, I was going to statically address the local inside interface, but then I was going to still have that edge router perform DHCP on the local inside area to all the devices that were going to be inside the local inside area. You know what I'm saying? So that edge router was going to do a lot of work. You know what I'm saying? Well, that DHCP server on the edge router was going to do a lot of work. It was going to dynamically allocate addresses to the local outside areas, and then it was going to do local inside on both area 1 and 2. So DHCP worked fine on the local outside, but I could not get addresses to the local inside. And that was pretty much all because I could not make adjacencies to the edge router. So the edge router and the area routers could not make adjacencies. And I was like, what did I do wrong? Did I mess up the wildcard address on the OSPF? Like, I was like going back and forth. I'm questioning. I was questioning what I had done. Especially, I was only focused on OSPF. Why OSPF wasn't working. Well, turned to find out it wasn't OSPF's fault. I had the wildcard address and everything else. Perfect. Everything on that, at least on that end, on OSPF's end, was fine. You know what I'm saying? OSPF I had it, even with all my crazy addressing that I was doing, it should have worked fine. What it was, though, was my subnetting plan. So if you remember, I gave the sub interfaces, and it was the sub interfaces. It wasn't the actual physical point-to-point link going to the router to the switch, so the edge router to the distro switch. It wasn't that. It was the sub interfaces addresses that I had allocated. I had totally allocated those, and I didn't figure this out. Well, I figured it out after I had closed the lab down, and I'm like, Joe, what did you do? What did you do? Like, why wouldn't this work? So if you remember, I gave those sub interface. I was giving all the point-to-point links, the 254. It was the 254 address. So that's only allowing for two IP addresses. All right. What that had done is because I had done that, I'm thinking about it now. Because I had done that, I had given it the 254 address. It wasn't the fact that it was only allowing 2 addresses, because it still should have worked fine. It's because how I set up DHCP. I set DHCP to the -24 subnet mask. All right. So that was 255.255.255.0 on the outside, the local outside interfaces. So I had told DHCP to allocate the local outside interfaces to the /24 address. All right, the subnet, the /24 subnet mask. All right, but the point-to-point link on the sub interface on the routers was in the 254, the /31 subnet. So when I had gone, and then we can take a look at the lab, and you'll see what I'd done. Um, if I had if I had just even if I had just either put those sub interfaces in the /24 subnet, or if I had told DHCP for the at least the outside the local outside interfaces to be allocated an address in the 254 range, then everything would have been fine. They would have got their one address left in that subnet to those edge routers, even though the point-to-point link was going through a switch. It was still there was no other there's no IP addresses on the switch, so that didn't matter. It's the fact that I had told DHCP one total subnet, totally different subnet than I had the actual link at, and that's what caused OSPF not to make an adjacency. Even though DHCP was still working fine because it was still getting those messages, and it allocated it out and whatnot. Pretty weird that DHCP would still do its thing, but DHCP does what it needs to do. You know what I'm saying? But yeah, I was like kicking myself in the to cookies after the fact because I just could not believe I couldn't believe it. I was like, after all this subnetting, what did you do wrong? And I was trying to be so conservative about what I did, and yeah, I thought it was pretty funny. I thought it was pretty funny. Well, I thought it was funny at least. You know what I'm saying? But the good part about doing stuff like that and making big boo boos in your topology. The good thing about, at least for me, is then I have a chance to go back and diagnose and troubleshoot what went wrong. So it almost gives me a scenario of, here's a topology that should work. Why isn't it working? Find out all the reasons why it's not working. And then, kind of like backtrack everything, go through the configurations, take a look, and diagnose what went wrong. So honestly, it gave me the opportunity to come up with a couple answers. You know what I'm saying? I had, there's a couple options there. Either I go back to DHCP in the edge router and reconfigure it to dynamically address to the 254 to the /31 mask for those area routers. You know what I'm saying? For the local outside interfaces. If I had done that, wham bam, thank you ma'am, it would have worked fine. It would have addressed a totally different address than was on there, obviously to support that last IP address in that particular subnet, and then OSPF would have again made its adjacency. Or I go back to the sub interfaces, which I actually did because I was like, no, let me just go back to the sub interfaces real quick and just play around with that. And that was my first actual step. And I went back to the sub interface and I changed it. I kept the address the same, but I changed the subnet mask to the /24. And the moment I changed to the /24, boom, OSPF made its adjacency to area 1. So I was like, all right, I know what I did wrong. You know what I'm saying? So it gave me the opportunity, again, to just, educate myself, again, on how to just, okay, take a step back. Let's take a look at the topology and then, figure out what happened. It's instances like that I love making mistakes like that. Again, just to the sole fact for me, so I can go back into that lab and then, let's make this topology work. You know what I'm saying? So, again, it was a great, I should have streamed it yesterday, but, I was totally beat up. I just wanted to, I was like, I was like, I need to figure this out, But like I said, these overnights, man, I tell you, I gotta get used to these. I'm not working tonight though. Tonight and tomorrow night, so I have some plans, baby. I also got a surprise for all of us too. I was gonna try to put it together today, but like I said, I worked all night, and I just actually woke up not too. I woke up what is it, about 5 o'clock my time now. I woke up at 3 o'clock. I had to whip together. I had to get dinner together for the kiddos. So the wife's at work, so I just got dinner. I just got dinner together real quick, and then obviously now I'm here with you guys. So, no, I was gonna say. So yeah, so we have a plan. We have a plan for today. Because we need to push on. We need to get past. We need to get past subnetting and all of these in just this part four this part four of the book here. That way we can, you know, we need to really make a good push today, to get past these parts, because I think a lot of these next couple parts. Just grab the book. I apologize for yawning, guys. I'm sorry. Tell you, I'm all McJabbled up. You know, I'm not used to the overnights, so getting used to it though. But all right, so like I said, we need to make like a good hard push to get past part four. So if I'm looking at chapter 11 here, like I said, we kicked its butt pretty hard. Chapter 12. Ooh, stop it. Chapter 12 is analyzing classical IPv4 networks. That's something, I guess. Yeah, we'll touch on that. We'll see how much time we need to spend on that. That's covering classful network. So that's pretty much saying like that. Well, that's classful IPv4 network, and so class A, class B, class C. Class A obviously is the what is how many? What is it? It's pretty much 0.0.0.0 to 127.255.255.255. That's a class A network. And what that's pretty much saying is class A, there's 8 binary bits in the first octet. That is the network. All right. In the class A and classful IPv4 addressing. So the first octet, so the first 8 binary bits, designates that as a class A network, and then the other 24 bits of that address are all host. All right. So when you think about classful IP networking, it's pretty much saying you just have a class A, you have a class B, and class C. All right. And then obviously it's not thinking about classless IPv4 networking. It's class full. All right. I guess we should spend some time on that. Because we really haven't, I guess, talked about that yet. But I'll try not to spend too much time on that. And then we get some and then chapter 13 gets into analyzing subnet masks. Again, that should be an easy one for us to just get through, guys. Because again, we've spent a lot of time subnetting together. Yeah. We should really get through that easily. And then chapter 14, analyzing exiting max. I'm just reviewing the actual physical book real quick, guys. Alright, now. We'll probably spend just a little bit on chapter 14. Just because it will be pertinent for us to, it'll help make the circle complete on subnetting and whatnot. So chapter 14 just brings everything brings everything back around and helps us complete our subnetting adventure here. All right, but then yeah, so then the next part would be chapter 5, and I want to try to get into chapter 5 this week. So again, I'm gonna try to make a hard push. I don't care how long we're gonna have to stream for, but we're gonna make a real hard push to get to chapter 5 because we got to get caught back up on things here. Chapter 5, part 5 here is obviously it's IPv4 routing. That gets into operating Cisco routers, configuring IPv4 addresses and static addresses, IP routing in local area networks, troubleshooting IPv4 routing. And the thing is, guys, we have been as a group here, we've been really tackling this throughout the labs that we've been doing. So for the most part, we should be able to breeze right through part 5 with really no issues. And then I can't wait. Oh. And then we got part 6, that's OSPF, guys. Awesome sauce. I can't wait to get into OSPF just to at least kind of establish more of the fundamental knowledge about OSPF. So that would be coming very, very shortly, guys. I can't wait to get into OSPF again, just to really nail that knowledge down. And then the one I'm not looking forward to is part 7. No, that's the start of IPv6. No, my head's gonna hurt so bad. But we got to do it, guys. We got to do it. So, so that hopefully we can make a good hard push this week. So that way by next week we can finally get into IPv6 discussions here. So we're gonna try to make a real hard push to get through these next couple parts. That way by next week we can start on IPv6. And then honestly, once we get past IPv6, guys, it's almost like smooth sailing. Well, I wouldn't say smooth sailing, but we get into more. We're gonna start getting into some more nitty gritty stuff. So we got wireless LANs coming up. That would be solely on Packet Tracer, guys, because there's no way I can't emulate wireless topologies without making a real wireless topology in my house, and I don't want to stop messing with my own house's Wi-Fi. So that would be a Packet Tracer. That would be all Packet Tracer labs right there. Which is fine, guys. I love me some Packet Tracer. Yeah, wireless is actually going to be pretty cool, I think, for us guys. Because yeah, wireless is going to be pretty cool. We've got some stuff to do. Oh, and then we're going to get into quality of service. Woo, quality of service. You know what's funny? After that, though, that ends it. Well, that ends the first book for us, guys. Yeah, so we're making progress, guys. You know, you might not think we are, but we actually are. We're making some serious progress here. Oh, excuse me again with my yawning. Alright. So, like I said, swear fingers. Yeah. Let me just finish my coffee real quick. How's everybody doing now? Hope everybody's doing good out there today. What's up, baby? I love my wife. My wife's awesome. I love you, baby. Mwah. It's always frozen for her. It's frozen. I never freeze. Let me shout. Let me give my wife a hug real quick. Ooh. Ooh, I love her. Gotta give my wife a virtual hug. She's at work right now, guys. Shout out to my wife. She's my working girl. Ugh, eating coffee grounds over here. All right. What do I do with all my stuff? All right. All right. Just take a nice sip of coffee. All right. I hope everybody's ready to study. It's study time, guys. Where's my mouse? Where's me mouse? Here's me mouse. That crazy mouse is always getting away on me. I gotta have a mouse trap. I'm gonna get a mouse trap for my mouse. What we're gonna do? Remember, like I said, we're gonna have to do a quick review, guys. I'm all about reviews. I'm all about the reviewing. Let's see something. Okay. I'm just looking at something real quick, guys. Don't mind me. Hey, don't mind me, huh? I'm just reviewing this. I'm just here. Like, I'm just looking at this real quick, guys, and then just doing a quick review. Yeah, might as well join you guys. 222 0 222.225 Did I put it? What did I put wrong? It's 255, 255, 255. Oh, beef caked it right there. It's okay. 192, 0, 2, 8, 0, 0, 0, 200.5.18, 0, 200.5. 50 50.0.0, 50.5.5, 2, 0, 2, 0, 0, 1, 0, 2, 0.0.25. I shall what I put mine. Oh, 191. Stupid. Alright. Let's go to another exam. We're reviewing real quick. Exam. So let's go over to the actually, yeah, let's go over to the whiteboard real quick, guys, so we can do a more better review on this one. Grab my stuff. I grabbed all my stuff. That other one, I was just trying to take a look because I wanted to see if it had the where you get to choose the where it wants you to find like the first address and the last address available in the subnet range, but that wasn't what it was. That was just actually classical IP addressing. So, burp. Just gonna do just these 10 questions, guys, and then we're gonna move on. And then we're gonna review. We'll do a review of everything real quick, of all the other chapters that we've done, and then we're gonna continue on to chapter 12. Like I said, we gotta keep reviewing, guys, and just keep logging away. The only way we're gonna retain this stuff. Okay. Where's my handy schmandy? My handy schmandy markers over here. Nah, got a hole in my pocket. Nah, that's what she said. Do I have a hole in my pocket? I do have a hole in my pocket. It's my secret hole. Don't put your hands in my pocket. That's what that tells you. All right. I think I'm gonna need some more coffee, guys, before I lose my noodles. Burp. All right. What do we got? 2.5. 2. What's our address? 192 68 4759. All right. All right. So 192 minus 256. 4. So what do we got? 64. All right, so 64. All right, let's take a look right here. How many times does that go into 64? So we got 0, 64. It falls right in the middle. All right, so Our subnet ID is 168.47.0. All right. Now, right here, we minus 1 from there equals 63. All right. So our broadcast address is 192.168.47.63. All right. So subnet ID and then subnet broadcast address. Okay. Oh, should we turn it on, mate? No, just come back. Baby, come back. Ooh, don't want to get a copyright strike. 0.192.168.47.63. All right. Working out my subnet. Jeez, I gotta stop putting it in that pocket. All right, put it all in this pocket. This pocket. All right. 25, 25, 54, 172, 30.1.1. All right, so we have 0 here. That turns into a 0. All right, 256 minus 254. So we have 2. All right, so they're going to go up in increments of 2. So we have 0, 2. Obviously, this falls in between 0 and 2 here. All right, so that's going to turn back to a 0. 30.172 is our subnet. So that's our subnet ID now. All right, so we're going to take away 1 from there. All right, and that's obviously going to be a 1. So now our subnet broadcast address is 172.30.1.255. All right, because remember, even though, again, this octet is zeros right here, the rule is when we have an octet full of zeros, okay, to get the subnet broadcast address right here. So this is actually going to get full of binary ones on this octet right here, guys. Okay, so 8 binary ones equals 255. So 172.30.1. All right, remember we got the 1 from here. Dot 255 is our subnet broadcast address. Don't put it in the right pocket. Put it in the left pocket. All right. So 230.0.0 172.30.1.255. All right. Good. Let me just take the red marker out of my pocket there. What do we got? 255, 255, 255, 128, 172, 6, 0, 17. All right. So obviously we have no octets. No octets of zeros. All right. So this is we have our interesting octet here. So 256 minus 128. All right. Obviously it's 128. It's pretty much just itself in half. All right. So 116 minus that. So it's 120. Yeah. 4, 2, and then 128. So it's just 128. So now it just goes up in increments of 0 to 128. So we go 0, 128. Obviously 17 falls in between here and 128. So you just minus 1 from that. You get 127. Now let's come over here and get our subnet ID 26.0.0 and then 172.26.0.127 is our subnet broadcast address. Okay. Don't put it in the right pocket. 255, 255, 248, 0, 172, 28, 250. Alright. 0, so 0, 256 minus 248. If I could write tonight. Minus 248. Alright, carry that. 16, 8. That's 4 now. 0. Alright. So 8. So we're going to go on increments. So we're going up in increments of 8. So how many times is 8 going to 250? So we're going to have to do the 8 tables. Alright. Blast this out real quick. 250 divided by 8. 31. 31 times 8. 248. So yada yada, 8 and a whole bunch, so we get to 248, and then, yeah, then it's 256, obviously, 256. All right, so all we have to do is, so this would be our ID, 248, I can write that right, come on. 248, 28, so 172, and then 172, 28, 255.255 is our subnet ID. Because remember, then we take the next one, minus 1, that's 255. All right, this one gets full of binary ones, turning that into a 255. So 172, 28, 255.255 is our subnet broadcast address. Okay. So 172, 28.48.0. 72, 28, 255, 255. Right. Did it fall in my pocket there? 255, 255, 255, 240. Now we got 192. 168. What do we got? 0.25.55. All right. So again, 256 minus 240. All right. So what do we got? 6, 1. So we got 16. So we just got to find the increments of how many times. So 16 goes into 55. So 16, 32, 48. What's the next one? 48, 16. Is it 50? Yeah, it's 54. Yeah, it's 54. Man, I'm horrible at math, guys. I tell you. 16 plus 16 plus 16 plus 16 plus 16. 64. 64, Joe. You're horrible. Horrible, I tell you. Horrible at math, man. It's embarrassing, honestly. I don't know if it's just because I'm tired or whatnot. Who knows? I'm not going to make excuses. All right. Either way, we fall into, so 48 is going to be our, so 192.168.0.48, and then we come over here, minus 163. At least I know the processes. How's that, guys, huh? I can get you anywhere because I know how to get there. I know the processes to pretty much anything, so. Just got too much in my head sometimes to remember. I don't like it. Excuse my language. 48, 192, 168.0.63. All right, let's keep it moving. Oh, look at that. We did them all. All right. All right, that completes that one then. Let's go over. Let's do a review now. 1, do them all, go down, chapter 1, chapter 2, chapter 3, chapter 4, chapter 5, chapter 6, chapter 7, chapter 8, chapter 9, chapter 10, chapter 11. All right, no more than, we're gonna give ourselves 15 questions. Didn't you break on me? It did. Epic Pen is like epically failing lately. I swear, ever since they did their little update. Not happy. Not happy with you, Epic Pen, right now. Paid money for you, buddy. I paid money for something. Better work. Alright. Which of the following terms represent a layer 3 on the OSI model, which includes the network header, encapsulated data. All right, so what are we going to say? We're going to say paquete. IP functions at which layer of the OSI model? We're going to say network. The diagram refers to which type? So that's multi-mode. All right, refer to the diagram. The new connections that is going between campus 1 and campus 2 routers require at least 500 megabytes per second bandwidth, and the routers are located 3,000 meters away from each other. So we're going to think big. We're going to think Zulu. All right. Boy, come on. Okay. All right. The network diagram uses Cat5 cabling, RJ45 connectors. Which of the following statements is true about the wires inside of the cabling? All right. So remember, we're going to think logic here. All right. The cabling between SW2 and S1 connected. Nope. The cabling between S1. Nope. PC1. Yep. They're connected on each. So the pins. Remember so from PC to switch or router to switch, it's straight through. Okay. Switch to switch is crossover, okay, or switch to hub is crossover, okay. That one's wrong. This one, gonna choose 3. Yep, that one's right, and that one's right. All right, which of the following data link layer protocols are used to encapsulate data? So, PPP and HDLC. Which of the protocols finds an unknown layer 2 address of a known ARP? How does the receiver HDL frame know what has been encapsulated within the frame? It's in the type header. When a Cisco iOS command line is initially accessed via console telnet with no extra privileges, which of the modes? So you're going to be in user mode. All right, all host ports reside in VLAN 1 with no port security, nor static MAC addressings. Tables, entries defined. Host B remains powered off, but all other hosts can ping each other successfully. Later, host B powers up and uses and the user issues the ping to 10.1.1.4 command to generate host B's first network. Which of the answers describe how the frame is forward? So remember, pretty much it's describing that host B hasn't been turned on, but all the other hosts have been turned on. So host B hasn't. It's going to be flooding out. It's going to be flooding that packet out because remember, it's trying to find where everybody's at because they just don't know. All right, so it's going to be sending out its ARP yarps. It's ARP yarps. All right. So the frame would be forwarded out SG. Yes, it will be. The frame, nope, it's going to go there. The frame will be forwarded to host D. Yep. After power on, a frame arrives at a switch. The switch has not yet learned the source MAC address of that frame. Which actions must the switch take in this case? So remember, the switch records when a frame comes in, the switch records the source MAC. So it records what interface or what port that came from, from the source. So it takes the port interface and the source MAC address off of that. All right. The switch checks the frame for loops. The switch adds the source MAC address to its MAC address table. Yes, it does. Nope, nope, nope. All right. Which answer encrypts the password that will be required of a user after the types of that'd be the enable. So encrypt's a special one. So we do the enable secret that makes that password to get into exec mode. It encrypts it. All right. Because if not, you can do a password to get into a user to your exec mode, but it'll come up as clear text when you take a look at your configurations. So you don't want that. All right. The exhibit shows some configuration commands that sit in a text file. After adding the configurations to the switch, the user will attempt to connect with the username Fred and password Hope. Which of the following best describes the accuracy of the configuration for the following? To do the subnet SSH. So let's take a look. Host name, good. IP domain, yep, so that's good. Username, Fred, and password Hope. Crypto key generate, very good. VLAN, so that's correct. Yep. So it's got a management VLAN with an IP address, so they can get into it. Very good. Transport, SSH, and Telnet, very good. So, but right here though, they didn't do the login local. So without doing the login local, this username and password combo, it won't work. All right. So they needed the login local. All right. For the exhibit, based on the information shown in the exhibit, what can be said of the configuration of the Gigabit 0-4's interface? 0-4. It's been set to half duplex and speed 100. Speed 100, half duplex. All right. Refer to the diagram. Both switches are Cisco switches. What would be the state, speed, and duplex to the link referred in S1? So obviously switch 2, somebody already went into switch 2 and set it speed 1000 and duplex full. So pretty much they turn that. By doing that, you enable auto negotiation. So switch 1 over here, it fails because of that. Well, it doesn't fail, but it just auto negotiation fails because switch 2 is not using auto negotiation, but it would still be up and full. All right. All right. Pretty much crushed that out real quick. All right. That's good. That's good. All right. All right. That was just a quick review, guys. That really didn't get into anything STP or nothing like that. Kind of disappointed, but I didn't want this to be too long because we gotta beat up on some chapter 12 here. So that's good for now. But we're gonna continue on doing these reviews as we go, guys. So let's carry on. Let's carry on the good fight. Let me just get my Epic Pen back up again. Come on, Epic Pen. See if it's broken again. There it goes. Hey, Epic Pen is working. Even that thing breaks on me. All right. So, chapter 12. Here we go. Analyzing classful IPv4 networks. So classful. So that's thinking about the actual. When I guess when they planned all of this, they had in mind, the classes, and that's what this chapter is just gonna dive into here. All right. All right. Analyzing classful IPv4 networks. When operating a network, hold on 1 second, guys. Thanks, guys. I need to make a coffee run. Need to have my daughter make me some quick coffee. Thank you, guys. Somebody get her? All right. Let's continue on here. All right. So, like I was saying, when operating a network, you often start. Why is this frozen? I never freeze. All right. When operating a network, you often start investigating a problem based on an IPv4 address and mask. Based on the IP address alone, you should be able to determine several facts about the class A, B, or C network in which the IPv4 address resides. This chapter lists the key facts about the classful IPv4 address and explains how to discover these facts following that. This chapter lists some practice problems before moving to the next chapter. You should practice until you're consistently determining all facts and quickly, confidently, based on the IP address. Okay. Let's do this. I know already. All right. Which of the following are not valid Class A networks? So remember, the Class A network is from 0.0.0.0 to 127.255.255.255. All right, and then Class B, 128.0.0.0 into 191.255.255.255. And then you got the Class C, which is 192.0.0.0 to 223.255.255.255. And then there is some reserved addresses. That's the 127.0.0 to the 127.255.255.255. So that's a reserved address, pretty much plucked out of the Class A address. And then you have a Class D and Class E, but those are both, I believe, reserved for some other case uses. And this chapter actually will touch on that too, I believe. Which of the following are not? So let's come over here. Let's turn it pink. I like pink. Pink, pink, pink. All right. So we're going to say 1. So we're going to say B already. B. And we'll just say C, because I know it's trying to trick me now. So, like I said, the 127 it's plucked out of the Class A class network there, and that's a reserve. That's pretty much like a reserved local. It's like a loopback, almost like, I believe it's like a loopback address or something like that. But it's gonna get into more of that here soon. All right. Which of the following are not valid Class B network IDs? Which of the following is not a? That one's good. Which of the following? Which of the following, man? Honestly, they're all good. Right? I think they're all good. I have a question on C though. C might not be. C might be one of those funky reserved ones, but we're gonna go with E. Which of the following are true about IP addresses? The IP address 172.16.99.45's IP network. Choose two answers. The network ID is 172.0.0.0. Choose two answers. The network is a Class B network. It's a Class B. The default, nope, it's not that. The number of host bits in the unsetted network is 16. Yes, it is. So it's B, and D. Which of the following are true? Just not look at those answers. I don't want to see them. Yeah. Which of the following are true about an IP address 192.168.6.7's IP? Choose two answers. That's not the network ID. The network is a class B. Yes, it is. All right. No, it's a class C. Not class B. Yeah, it's a class C. Jump. The default is, yes, that's the default. It's 255.255.255. Yep, /24. The number of host bits in the upsetted network is 16. No. So there's one more. So it would be A. Yeah. It's A. Because given the fact that a class C network, the default mask is 255.255.255.0, and then given the fact that it states that the IP address is 192.168.6, that's the network. .7 is the host. Okay. Let's not scroll all the way down. Which of the following? Get my thing again. Which of the following is a network broadcast address? Which of the following is a network broadcast? So it's not A. It's not B. Gonna say. I'm gonna say D. Come on, Pen. Come back to me. Baby, come back. So 5. I'm gonna say D. All right, because the default mask for a class B is 255.255.0.0. So given that information, 172.30 network, 255.255 broadcast. Okay. Let's see how we did here. Good, 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 and good. Woo, baby! All right. I gotta run the bathroom, guys, real quick. Give me uno momento, por favor. I'm back. How about that? All right. Looks like we did pretty good. I am happy about that. All right. All right. So I think we have again, we have a good understanding. So we're not going to spend too much time on this chapter. Like I said, I want to breeze through this. I want to breeze through this chapter. But there are some stuff though we should cover though. So classical network concept. Imagine that you have a job interview for your first IT job. As part of the interview, you're given an IPv4 address and mask of 10.4.5.99.255.255.255. Okay, so what that statement tells us is this part right here, all right, that's the actual network, okay, and that's governed by this mask, okay. All right, let me clean that up real quick. Let me actually make this a little bit smaller. All right, like I said, so this mask right here, tells us that 10.4.5 is the network, okay, and then 99 itself, all right, 99, that's the host bits, because 0 right here is 0, okay, so that just tells us that, okay, very good. All right. What can you tell the interviewer about the classical network? In this case, the class A, in which the IP address resides. This section, the first two major sections in this chapter reviews the concept of classical IP networks. Okay, in other words, class A, class B, class C. In particular, this chapter examines how to begin with a single IP address, and then determine its facts, class A, class B, class C, default mask, number of networks, octet bits, number of host octet bits. Yeah, okay. Number of network octets, number of host octets, number of host addresses in the network, network ID, network broadcast address, first and last addresses used in the network. Okay, so remember, if we have a address from 0, all right, 0.0.0 to we're gonna say 126.255.255.255, because remember 127 to, so here we go. Let's do this then. So if we have an address from 0.0.0.0, all right, to 126.255.255.255, all right, so that's pretty much stating, even though it's in itself it says to 127 to the thing, but the thing is 127.0.0.0 to 127.255.255.255 is a reserved address plane. All right, but then we have the 172. Okay, we have the 172. 172.0.0.0 to what is it? 191.255.255.255. That's class B. And then we have 192.0.0.0 to, what is it, 223? Is it 223? I think it's 223, right? It's 223. 223.0, 255.255.255. You know what I'm doing here? I'll even fix this just so we can be on the legit same page of what this chapter is going to cover. Even though, like I said, the 127 to 127.255.255, that in itself. Oh, I skipped the whole address plane, didn't I? Yes, I did, Joe. It's 128, right? Yeah, 128. Man, I'm stumbling over. So yeah, so 128. So 0.0.0 to 127.255.255 to 128.0.0.0 to 191, and then 192 to 223.255, and then it picks up to 24.0.0.0 is a class D, and that goes to, what does that go to? 239, yeah, 239.255.255.255. Again, those are, I believe these two ranges are experiment. Well, I know for sure that the Class E network is a totally reserved address that you'll never see, because it's just not in use. Never has been and never will be. It was like reserved for like scientific or military operations or whatever. So, so we have over here, Class A, Class B. This is Class C. All right, and then this is Class D, and then Class E. All right. So yeah. All right. So like this chapter is gonna cover, guys. We have particular ranges that these networks are gonna cover. When you're dealing with a Class A network, all right, that what that's going to tell you when you have a Class A, all right, is this portion right here is going to be the host, the network, I mean. So this is the network, okay? So always in a Class A network, the network resides in the first octet. The network resides in the first octet. So the first 8 bits in the network, all right, are going to be network bits. Everything else after that is all hosts. So this would be all hosts by default, okay? This is unsubnetting class full network, all right? And a Class B network now, the first 2 octets, all right? So you have 16 octets in a Class B network that are going to be by default, all right, the network bits, and then you have 16 other bits. So the last 2 octets, okay, those will be host, okay? And then on the Class C, the first 3 octets are the default network. So the first 3, so the first 24 bits of the network of a Class C network is the network part, and then the last part are the host bits. That's why when you see the 192.168.0 or .1 or whatever, it usually follows the /24 subnet mask, because it's residing within a Class C network. All right, that's why when you see the 192.168.1. whatever, it's usually followed by a /24 subnet mask or a greater subnet mask. Okay, because the host part usually resides somewhere in this octet. Okay. All right. So that's when you see, and this is, so I'm talking about private IPv4 addressing. Okay, not public, private. Okay. And again, when you see the private 172.16 network, all right, the 172.16 to 172.31, that would be like a class B private. That's why you'll see the 172.16, and then you'll see some host bits, but then it'll proceed by like a /16 mask or something a little bit greater than 16, but usually a /16. All right. But again, if you choose to manipulate a Class A network, usually, that would be the 10. So the 10.0. whatever network, so it's the 10.255.255. You'll see this 10/whatever dash subnet mask 18. Dash 8. I mean dash 8. All right. That's why a Class A network, even a private Class A network, you have so many more addresses to manipulate within a Class A network, okay? Because by default, the network bits only reside in the first 8, okay? And then you have 24 host bits to manipulate after the fact. So we can subnet these 24 host bits, okay? we can only subnet out of a Class B network 16 host bits, and then we can only subnet a Class C network with 8 host bits. Okay, all right. So that's kind of how that works. That plays out right there. Hope that kind of makes sense for everybody. All right. All right. Let's continue on. So there's some of the classes. So 1 to 126 unicast, 128 to 191 unicast medium size, 192 to 120 to 223 unicast small, and then you got some multicast addresses. So there it even states right there. So all right, so 224 to 239, that's multicast addressing, and then the 240 to 255, that was a Class E right there. That's obviously reserved for experimental purposes, and again, you'll never see those out in the wild, so they just don't exist. They're just not used. How's that? Okay. That was fast. You are like the fastest coffee maker I've ever seen, honey. Thank you so much, baby.
Been getting better and better.
You are too. Thank you, sweetie.
Okay.
Appreciate that. What's up? No, you're good, baby. Thank you so much. I love my daughter. My daughter's awesome. She's the fastest coffee maker in the West, guys. I tell you. The fastest coffee maker in the West. I love my kids, guys. My kids are amazing people. I have to tell you guys, my kids are the best people I've ever met in my entire life. They're awesome. Every single one of them are awesome people. They're gonna grow up to be better people than I was. So I'm so proud of that. Almost makes me cry every time. All right, let's continue on here. Let's get it back into it. So Class A. So there's some, but it's just pretty much going over the facts, of how to pretty much distinguish the networks. Why is it minusing? That's fine. I'm just looking at some stuff, guys. All right, like I said, it's just going over exactly what we just talked about. Note that the address ranges of all addresses begin with the 0, and all addresses that begin. So note that all addresses note that the address ranges of all addresses that begin with 0 and all addresses that begin with 127 are reserved. All right. They had not been reserved since the creation of Class A, as listed in the RFC 791, published in 1981. Then they might have been known as the Class A network 0.0.0 and 127.0.0 because they are reserved. However, the address space has 126 Class A networks, and not 128. Oh, okay. Oh, all right. So that clears that up. So the 0.0.0 network, so the 0.0 network, and like I said, there's a couple of addresses that are reserved within within the Class A network. Okay, and that's just one thing. It's like a sidebar note that you have to remember. So in the Class A network, the network 0.0.0.0, all right, and not through, and the network 127.0.0.0. So that's pretty much stating. Let's write this down. So 0.0.0 through 0 to 255 to 255.255, and then 127.0.0.0 through 127.255.255.255. All right, these are reserved, okay? All right, so these are reserved addresses, okay? These addresses, all right, are reserved, all right? All right, so you won't be using these addresses, okay? That's why you'll see like the 127, like on, probably on like, does that get used as a loopback address? I think it does on like Windows and stuff like that. Well, just in general, I think the 127 gets used as like a loopback address on some devices as just like a default loopback address, just because it's not used. All right, but so the zero network all the way to 0.255.255.255. So that's pretty much establishing that that whole entire network is gone. All right, same thing with the 127. That whole entire network is gone. All right, but then the 1.0.0.0 to all the way to 126. So then the whole thing though picks up here at 1.0.0.0. All right, through 126. All right, 255.255.255. All right, this is the usable. All right, the usable range. All right, this would be the usable range of that Class A network right there. All right, so from 1 all the way to 126.255.255.255. That is that usable range of the Class A network. Okay, that's all that's stating right there. Okay, so again, let's move on. All right. In addition to the reserve of that would be the another purpose is other newer RFCs also reserve small pieces of the Class A, Class B, and Class C address spaces. So the table like 12D will, with the count of the number of Class A, B, C, are a good place to get a sense of the size of the network. However, the number of reserved networks does change slightly over time based on the address ranges. So again, this is just knowledge to keep in mind, but this doesn't affect how you are going to be addressing your enterprise network, because again, we're going to be using what is the terminology I'm looking for? There's a certain term. It's classless interdomain routing. CIDR. We're going to be using CIDR. Classless interdomain routing. Right? CIDR. So we're going to be using, because we're going to be using CIDR in our enterprise networks, these address ranges shouldn't affect us, because remember, we're going to be using the Class A 10 network, all right? So 10 to 10.255.255.255, all right, which again gives us 100, it gives us like 126,000. It gives us an exorbitant amount of hosts, all right, to manipulate, and it gives us plenty of network space to subnet out. And then we have our Class C network, which is 172.16 to 172.31.255.255.255. And then we have our Class C network, which is 192.168.0.0 to 192.168.255.255. All right. So we have those are our classless interdomain private IP ranges that we're gonna be using on our own. All right, this is more on the private IP routing. All right. Hopefully I'm making sense of that. So that's it. All right. The number and sizes of Class A, B, C networks. The table lists ranges of the Class A, B, C networks. However, some key points can be lost. Just referencing a table of information. This section examines the Class A, B, C network. Focus on more important points in the expectations and unusual cases. First, the number of networks for each class slightly differs. Only 126 Class A networks exist. Network 1, again, 1, 2, 3, and so on. Like I said, remember 1 all the way up to 126.25.25.25. However, 16,384 Class B networks exist with more than 3 million, with more than 2 million Class C networks. Okay, so that number just keeps on growing. Next, note the size of the networks for each class also slightly differ. Class A network is a relatively large with over 16 million host IP addresses. Okay, 16 million. Let me say that again. 16 million. It's a lot of hosts. Okay, 16 million IP addresses per network. They were originally intended to be used for the largest companies and organizations. Class B networks are smaller with over 65,000 hosts per network. Finally, Class Cs are intended for small organizations, have 254 hosts in each network. Okay, so that's how when they originally created IPv4. That's what the thought was to pretty much establish these ranges for the companies that particularly needed these the sizes. They weren't thinking, I guess, like the thought was, why is this so hard to pour? Obviously things changed. The internet changed. What's going on with my coffee? Sorry. Coffee's coffee nonetheless. Obviously, everything expanded rapidly after the mid '90s with the internet boom and the home PC became more and more common. All right, when at first the home PC wasn't commonplace. All right, and then obviously cell phones and everything else followed suit. Laptops, smart devices. Gaming consoles and everything else, all requiring an IPv4 address. So, all right. In some cases, an engineer might need to think about a Class A, B, C network as if the network has not been subdivided through the subnetting process. In such case, the address in the classful network has a structure with two parts. The network part, sometimes called the prefix. All right, so that's where like you'll hear the prefix terminology is when like they're thinking about class full networking. Okay, so the prefix that's like the terminology they'll use when they're talking about the network portion, and then the host part. So two parts in classful networking, they think about two parts: the network part and the host part, the prefix and the host. All right. Then comparing any two IP addresses in one network, the following observations can be made. All right. The address in the same network have the same values in the network. The address in the same network has the same values in the network part. The address in the same network has different values in the host parts. Cool. For example, Class A network 10.0.0.0 by definition, the network part consists of the first octet. Yep. As a result, all addresses have an equal value in the network part, namely the 10 in the first octet. If you then compare any two addresses in the network, the addresses have different values in the last three octets. For example, the IP address 10.1.1.1 and 10.1.1.2 have the same value in the first octet in the network part, but have different values in the host part. All right, so that's just establishing that in Class A, first octet by default, all right, is 8 bits. It's the first octet, 8 bits long, okay? The last 3 octets, the last 24 bits in that IPv4 address are the host bits, and that's what's going to be different. That's what's going to continue to change, okay? But the network part will stay the same, okay? All right. Yep. Although we humans can easily understand the concept behind figure 1012, computers prefer numbers to communicate those same ideas. Woo! Copy. To communicate those same ideas, each network class has an associated default mask that defines the size of the network and host parts of an unsubnetted class ABC network. To do so, I skipped too far. All right, to do so, the mask lists binary ones for the bits considered for the network part and binary zeros for bits considered to be in the host part. So that's where that's where that subnetting comes in. There had to have been a way. They had to make a way for computers to understand where the host bits and where the network bits fell into that actual address. So they needed to create that subnet, so that actual subnet part that what are they going to describe it as? So the mask. So they're going to call it the masks. So the mask, all right? Let's just call it the mask. So they had to create a mask, all right? All right. So we have our network, all right? 10 dot whatever, all right? We needed a way for a computer to understand where the host, where the network resides, okay, network, all right, and where the host reside within that 32-bit range, okay? We needed a way for those computers to know. So that's when they created the mask, okay? And the mask pretty much states that if there's all binary ones, 1, 2, 3, 4, 5, 6, 7, 8, all right, that tells the computer that this is the network portion, okay? But then we have 0, 0s, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, so on and so forth. That's just telling the computer that in here, in this part, this all resides the host, okay? All right, so that's what that mask does, okay? So this is the mask, okay? All right. Now, as the network engineer, we alter the mask, all right? Obviously, we can't, depending on where we're at, we can't say touch the network portion. We have a network portion that we still can't touch, but we could take this host mask, all right, host mask, all right, and then we can start assigning binary ones in parts, inside of this host mask, okay, to then give back to that network part. So then the computers know that, okay, so this is now a new network chain, not network chain, but new network. Again, we're going to assign more binary ones. Okay, now this is part of the network, all right, and then we'll just give this a couple ones. So somewhere in this part of the host bit resides some network part, okay, and that's how this concept was created, and that's why it was created, to do this. All right. And here we go. Here's a great depiction right there. Same thing. All right. Same exact thing with the concepts. Okay. Decimal 255 converts to binary 1111111. Decimal 0 converts to 8. Binary is 0 to 0 to 0 to 0 to 0 to 0 to 0. All right. So, number of hosts per network. Calculating the number of hosts per network requires some basic binary math. First, consider a case where you have a single binary digit. How many unique values are there? There are, of course, 2. So 0 and 1. 0 and 1. On or off. 0 and 1. All right. You can't. Here we go. Let's do some binary real quick. All right, I love this. All right, all right, all right. So we have on and off, on and off. All right, these are my binary bits. So I got 1, and I have 0. All right, 1, and then I have 0. All right, this is binary. Okay, this is as simple as it gets. This is, all right, this is how, computers know, what they're doing. All right, on 1, 0, 1, 0, 1, 0. Okay. Is that even showing up when I do it? It's not even coming on the screen, is it? Oh, it does. There you go. Okay. Got it. All right. So that's binary, guys. Real easy. All right. Real easy. All right. All right. All right. Let's touch on something real quick. Well, we gotta touch on a couple of things. All right, let's touch on this. Calculating the number of hosts per network requires some basic binary. First, consider the case of where you have a single binary digit. How many unique values are there? There are, of course, 2, 0 and 1. So with 2 bits, you can make 4 combinations: 0, 0, 0, 1, 1, 0, and 1, 1. Okay. As it turns out, the total combinations of a unique value, you can make the n network bits is 2 to the n. All right, so 2 to the n. So that's where we get this equation from, where 2, because everything's in binary. All right, so we have the 2 to the. You're gonna see that repeated: 2 to the n, 2 to the h, 2 to the s, because we can only have those values in that particular bit. Okay, so host addresses, the IP address assigned to a host must be unique. The host bit exists for the purpose of giving each host a unique IP address. In venture of having a different value in the host part of the address. So the host part is 2 to the h. Unique combination exists. Okay. However, the number of hosts in the network is not 2 to the h. Instead, it's 2 to the h minus 2. Because remember, we have the 2 reserved addresses. So we have the subnet ID, and then we have the broadcast address. So we have the subnet ID and the broadcast address. So that's why you'll see the 2 to the h minus 2, because we have to remove those 2 reserved addresses, okay, from that equation. All right. Otherwise, host address, but still reserved 2 special. So one's for the network ID and the network broadcast address. So there you go. All right. So just key topic: 2 to the h minus 2. Okay, where h is the number of host bits. All right. Deriving the network ID and related numbers. Each class 4 network has 4 key numbers. 4 key numbers that describe the network. You can derive these 4 numbers if you start with just one IP address in the network. The numbers are as follows. So network number, first numeric lowest usable address, last numeric lowest address, and then network broadcast address. So again, if we were to give ourselves a simple equation, so say if we had the 10, let's just write the mask up here, 2 for 5. That's, well, we're gonna, yeah. Let's do this. So 2 for 5, 2 for 5, 2 for 5, dot 0. All right. Our address is 192.168.1, and we'll say, whatever 10. All right. So obviously, like we done, so 192.168.1.0, that would be our network ID. All right. Our network broadcast, on the other hand, would be 192.168.1.245. Remember, we got to fill these out with binary ones. All right. Now, to just find the first usable address within the range, we just plus 1. So we just add, all we're going to do, instead of finding the broadcast, all we're going to do is add one binary bit. So one binary bit to that last octet. Obviously, it's going to get us 192.168.1.1. All right. Now we come over here, 192.168.1.255. All we're going to do is minus one binary bit from that octet's range, 192.168.1.254. All right. So this will be the first usable address within this range. This will be the last usable address within the range. So we have 192.168.1.1, 192.168.1.255. So these first usable address, last usable address. All right. Broadcast network broadcast address. All right, and then network ID. Okay. All right. More copy. More copy. All right. Let's continue on. First, consider both network and first usable IP address. The network number, also called the network ID, network address, identifies the network. By definition, the network number is the numeric lowest in the network. However, to prevent any ambiguity, the people who have made up IP addresses added the restrictions to that network number cannot be assigned as an address. So the lowest number in the address is the network ID. Then the first numeric lowest host IP address, one larger than the ID is the first usable address. Okay. Next, consider the network broadcast address along with the largest numeric highest usable IP address. The TCP/IP RFC defines the network broadcast address as a special address in each network. The broadcast address can be used as the destination address in a packet, and the router would forward that copy to all hosts in that classful network. Numerically, a network broadcast address is always the highest last number in the network. As a result, the highest last number usable in the address is the address that is one less, so minus one less than the network broadcast address. So that's how we get the +1 to the network ID, gets us the first usable IP address within that network range, and then we get that the last usable IP address by using that other reference by saying, okay, what is the broadcast address? Well, one less than the broadcast address within that network ID gets us our last usable IP address. So that's how we get the 254 and then the .1. Okay. Simply put, you can find the network number and the network broadcast address by finding first the last usable IP address. In the network is easy. For the exam, you should be able to find all four values with ease. The purpose is as follows. So it's just stating define the class. All right. Secondly, mentally divide the network of host bits in one class. Find the network number. Change the IP address to the host to 0. To find the first, add 1 to the fourth octet. To find the broadcast, change the network to host to 255. Find the last, subtract 1 from the fourth octet in the broadcast address. The written process actually looks harder than this. Shows the example of the process used in the class A IP at network 10.17.18.21 with the circle and the numbers on how to, okay. So you guys have already sat with me and we've gone over this process a whole bunch of times, and it always equals out. So by our standards, again, we've beat this up quite a bit. Just can't shake this, guys. I'm trying my best. I will struggle on. We're doing good though. Once this coffee kicks, though, I'll be fired up. What movie, guys? Name me that movie. All right. It was actually one of my favorite movies growing up. Actually, still one of my favorite movies. All right. Yeah. So we've gone over this process again. Unusual network IDs and network broadcast address. Some of the more unusual numbers in and around the range of Class A, B, C networks. Numbers can cause some confusion. This section lists some examples of numbers that make many people make wrong assumptions about the network meaning of the wrong assumptions about the. Let me have a sheet. You guys can still see me, right? First, the Class A. First, the Class A. First, the Class A. The first odd fact in the range. 1 million text messages. First, the Class A odd fact in the range of the values. And the first octet omits the number 0 and 127. As it turns out, no, you guys can't see me. As it turns out, what would be a Class A network 0.0 was originally reserved for some broadcasting requirements. So all addresses that begin with 0 and the first octet are reserved. All right. What would be Class A network 127.0.0 is still reserved because of the special addresses used by software testing called the loopback address. So there you go. So that's what I was kind of referring to earlier, where that 127.0.0.1, that's what you're going to see it commonly as the loopback address. Okay, you'll probably see that actually on your PC or whatnot, or whatever you have. All right, you'll see that 127 address is the loopback address. Okay, all right. All right, Class B and C. Some of the network numbers can look odd, particularly if you fall into a habit of thinking that zeros at the end means the number of is the number ID, and that 255 N means the network broadcast address. First, Class B networks numbers range from 128.0.0.0 to 191.255.0.0. Okay. For a total of 2 to the 14th networks. However, the very first lowest number, all right, Class B network, all right, the 128 looks a little bit like a Class A network because it ends with all zeros. However, the first octet is 128, making it a Class B network. Okay, so that's all that's saying is still. Let me just do it on the board. Faster when I put it on the board, I guess. Woo! So even though again all it's stating is the even though we have the 128.0.0.0, and you might think that's a Class A network because you see here the binary 0, you see the 0, the decimal zeros here. Though it's a Class B, so no matter what, this is where the network is residing. Okay, the network still resides in 128.0. Okay, there's no getting away from that fact that this is a Class B. All right, and the network is still residing in the 128.0. All right, so that's the fact. So don't get confused when you see the decimal zeros. You still have to remember the fact that inside of a Class B network, no matter where the range is, I guess, on this octet, on that second octet, within the first 2 octets of that Class B network, the first 2 octets will always be network bits. Okay, that's all that's stating right there. Same thing here when you go all the way up to 191.255. All right, .0.0. All right, again, first 2 octets is network. All right, this will always be network bits. Okay, this is still the class B network right here, all right? These last two octets, again, host, all right? Host, all right? That's it, all right? For another example, the high end of class B range might look strange at a glance. Yeah, so the 191.255, but this is indeed the numeric highest of the valid class B numbers. The class network is the network broadcast address obviously would be 191.255.255.255. Might look a little bit like a class A broadcast address, but because of the three 255s at the end, but indeed it's the, yeah. So I'm gonna try not to confuse you guys as much as I'm probably confusing myself, but nonetheless, we're still on the same track here. All right, same thing here. Let's talk about a class C now. All right, so class C, remember, it picks up here, 192.0.0.0. All right, now again, somebody might look at this, because of the zeros that we have here, they might think that the network portion only resides here. But in fact, this is a class C. The network portion resides in these three octets, all right? Because there's 24 network bits on a class C network, okay? 24, all right? So the first three octets will always be the network part of a class C network, okay? That's what we're talking about. And then just this last bit right here will be host. All right? So don't get confused by looking at a class C network and then seeing the zeros and thinking that the network portion just lives inside of this first octet. It does not. The network portion lives in the first three octets of that address, okay? The first three octets of that address, okay? All right. Yep. All right, and the same thing at the very far end, you have the 223.255.255.255. All right. Again, the network portion, again, it lives here. All right, the first three, because again, it's this class C network. The first 24 bits of that class C network is all network. So this is all network. All right, just this last octet, this last 8 binary bits is host. All right, so this is always host. This though is always network. All right, so don't think when you see the 223 and you see all these 255s that you're still dealing with that these are host bits. All right, it's not. You can, even if you have the 223.255.0, all right. Again, this is just identifying the network. All right, this is just host. All right, so this would be the network ID of the 223.255.255 network. All right, because we have a 0 here. All right, that's it. All right, practice with classful networking. Yeah. All right. Guys, we crushed this one. All right, just some key terms: network, classful IP network, network numbers, network IDs, network address, network broadcast address, network part, host part, default mask. All right, some additional references. Yeah. All right. We crushed that. I'm good with that. I don't see anybody in the chat chatting it up. So, again, if there was any question, guys, just always ask me, guys. If I didn't cover anything good enough that you don't have an understanding at this point of where we're at, remember, we're talking about class full IP addressing, okay? Class full IP addressing, okay? This isn't classless IP addressing. This is class full IP addressing, okay? All right? So that's why we have to talk about it in this terminology, all right? Or in this, for instance. How's that? Grab some more. Now, again, we're going to keep moving, guys. We're trucking along. Remember, I want to get through I want to get through part 4 because I think we've spent enough time on part 4. And I myself, I have a good understanding. I hope you guys have a good understanding too. I know I'm pretty confident now. All right, chapter 13, analyzing subnet masks. Okay, all right. The subnet mask used in one or more subnets in an IP internetwork says a lot about the intent of the subnet design. First, the mask divides addresses into 2 parts, prefix and host, with the host part defining the size of the subnet. Then the class A, B, or C further divides the structure into addresses and the subnets, breaking the prefix part into networks and subnet parts. The subnet part defines the number of subnets that could exist inside one classful IP network, assuming that one mask is used throughout the classful network. The subnet mask holds the key understanding the subnet mask holds the key to understanding several important subnetting design points. However, to analyze a subnet mask, you first need some basic math skills with the mask. The math converts the mask between the 3 different formats used to represent the mask. Okay, so we have binary, dotted decimal notation, so DDN, and then prefix, also called classless interdomain routing. So you heard me say that earlier, CIDR, classless interdomain routing. Okay, again, when we're talking about like private enterprise networking, okay, when we're using NAT, okay, when we have one private address on our pretty much like our local outside interface, we're going to be using NAT on that local outside interface with one private addressing, and then on our local inside, we're using we're using private IPv4 addressing, CIDR, classless interdomain routing inside of our enterprise network, because it don't matter, all right? Because we're pushing all of that addressing. We're going to be using that one private address on our local outside by using that, all right, to then reach out to the internet, and then obviously for the internet to reach back out to us, okay? All right. So it's cool. We're going to be talking about CIDR in this chapter, it looks like. All right. Man, guys, I just get I apologize for drinking so much coffee. I'm just hurt up. Like I said, my body's still getting used to doing the overnights. All right. This chapter has 2 major sections. The first focuses on the mask format and the math used to convert between the three formats. The second section explains how to take an IP address and its subnet mask and analyze those values. And particularly, it shows how to determine the 3-part format of the IPv4 address and describe the facts about the subnetting design that are implied by the mask. Okay? All right. Let's take the do I know this already? Let's do the quizzy boys. Let's do the quizzy boys and girls. Hey there, boys and girls. That's creepy. I know. All right. Which of the following answers the list prefix CIDR, the CIDR format equivalent to 255.254.0? Okay, so we have 8, 16, and then 7. So 8, 16, and 7. So what do we got? 23. So it's got C, right? So 1, C. All right. And that's because what we're doing, again, 255.254.0. So we have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 0, 1, and then we have 0, 1, 2, 3, 4, 5, 6, 7, 8. All right. So all we're going to do is count the binary ones, okay? All right, so 8 plus 8 plus 7, okay, equals, all right, 23, all right? So that is our CIDR CIDR subnet mask, all right, notation /23, okay? All right. All right. Which of the following answers list the prefix CIDR format for equivalent to 255.240, okay? So let's do it. Let's do it to it. Let's do it to it. All right, 240, 255. All right. All right, so we have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. All right, so we have 8, 8. All right, so we have 16 plus 8. All right, 24. All right, now what do we got here? What equals 240? Okay, what equals 240? This is I'm gonna have these down pat. I guarantee by the end of it. Okay, so we have 1, 2, 3, 4. 0, 0, 0, 0. Okay, so 4. All right, so that'd be /28 CIDR notation. Okay, so 28. So 2 BB. All right. Which of the following answers list the dotted decimal notation, the DDR equivalent to /30? So /30. Okay. So again, so we can eliminate these two. Okay, because these. So this is obviously this is 24. This would be 23. All right. This one we have to. Let's just do the math real quick. Okay. Let's look for 30. All right, so we have 8, 16, 24, 25, 26, 27, 28, 29, 30. So 1, 2, 3, 4, 5, 6. All right, 0, 0. Okay, so if we have this in binary, this in binary equals 252. 252. Okay, all right. Again, I'm gonna have these pretty soon down pat. Whoa, what did I just press? Ah, let me press the freaking home button. Yeah. All right. All right. So it's 252. I swear, like I said, is anybody out there? Oh, who do we got? Who do we got, JB? I never freeze. I never freeze. I love you, baby. Hey, Dubs, what up, my man? What's up, buddy? Hey, Dubby Dubs. All right. I got 8 Dubs and my wife up in this place. I love it, man. All right, so, sort of, kind of, like, this is, like, I gotta start, I'm gonna remember, like I said, I'm gonna have this table remembered, pretty soon. So the table, pretty much, so here's the table. So you got 0, 128, 0, 128, 192, 224, 224, 240, 248, 248, all right. Let me just shoot. Yeah, let me erase that real quick. So 248, 225, is it 252? Yes, 252, and then 254, and then 255. All right. So 0, 128, 192, 224, 240, 248, 252, and then 254, and then 255. So this will always be your ranges. So obviously 0 would be all 8 binary zeros. 1, 2, 3, 4, 5, 6, 7, 8. And then this would be, this is going to be 1 binary 0, 1 binary 1, and then followed by 7. 1, 2, 3, 4, 5, 6, 7 binary 1s, and then 2 binary 1s, followed by 6 binary 0s, 2, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. 1, 2, 3. 1, 2, 2, 2. And then 1, 2, 3, 4, 5, 6, 7. 1. And then 1, 2, 3, 4, 5, 6, 7, 8. So that's how. That's the table right there, A-dubs. So there you go. So that's cool. Cool. How you doing today, my friend? I'm glad to see you back in the stream, man. Good to see you. So that's how we're gonna be going over today. But yeah, so we're blasting. I'm gonna try to do my best to blast through all of part 4, hopefully by tonight. We kind of just blasted right through chapter 12. We're gonna do our part to blast through chapter 13, just because I think by now, with all the subnetting and everything that we did over the last couple of days, I think we have this fundamental knowledge pretty down pat. But we're still going to be reviewing it for the fact of reviewing it. Oh, that's cool, man. Working and lurking, baby. Working and lurking. I love it. Dude, I tell you, man, I am beat up doing these overnight shifts right now. I am a hot mess right now. My wife has been commanding me to go to bed when I come home. That way I'm a normally functioning human being. Did you really? That's awesome, dude. I am so glad. You pump me up right now, A-dubs. You pump me up. I swear, if that makes me feel good that somebody was able to get something out of it. And if you were able to get something out of it, A-dubs, thank you very much for telling me that, man. You know, because that way how I kind of explained it helped me like, you know, the way I was going over it just in myself was helping me continue to understand it, man. And again, like I always say, if anybody can get anything out of what I do here, that just makes, even if it's one person, even if it's just you that gets anything out of me doing these streams, I'm so happy, dude. Oh, dude, thank you. I hate it. I can't wait. I'm trying to get a job at the post office right now. I can't wait to be done doing what I'm doing right now. I'm a cashier again. I hate being a cashier. But it's fine. A job's a job. I mean, I'll never discriminate on a job. That's why I don't care. But me being a cashier doesn't do too well for my mental capacity. Dealing with the public overnight makes for a grumpy Joe, I guess. Yeah. Right. I got you. Yeah, so subnet mask. So that's pretty much what we're covering. That's what chapter 13. So chapter 13, chapter 12 that we just blasted through, that was touching on the fact of class full. Okay, so class full IPv4 addresses. So you have your class A, your class B, and class C. And that was just saying, so in the class A network, so a class A network, class B network, and a class C. All right, I'm just gonna throw some quick examples up there for you, real quick, A-dubs. And I'll put some examples that you've probably seen before in your travels. All right, so in a class A network, remember this is class full IPA network. So class A will always be, the first octet will always be network. The last octets will always be host. Class B, the first 2 octets, okay? So 8 and 8, so 16 bits, okay? This is network, this is host, okay? And then Class C would be the first 3 octets, okay? So these 24 bits in the Class C network are always network, all right? And then the very last octet, only 8 binary bits, will be the host part of the yeah, people do suck, man. They do, especially when they go into the bathroom and they plaster the walls with shit all over the place, and then I got to go in there afterwards and clean up their nasty shit plaster. Again, doesn't make for a happy Joe at the end of the night. Well, in the beginning of the morning. But that's beside the point. That's why we're doing these, man. That's why we're going after these certs, so we can get a job, so we don't have to clean up plastered shit walls ever again. So, but yeah. So that's pretty much what chapter 12 was talking about. Okay, it was just class full networking and just getting over the concept of when we're dealing with these networks, we don't want to assume. Again, if we assume that 192.168, if we just look at that and we assume that that's network, we're making the wrong assumption. We have to look at it as a actual Class C network, okay, and involve that actual third binary bit in there. Same thing with the Class B, because you can have an address to the 128.0.0.0, and again, the 128.0. This is still a Class B network, so we have to remember that the first 2 octets in that Class B network are network bits, and those last 2 are host bits right there. So that's what chapter 12 is covering. Now, again, we're now getting into class lists or CIDR. All right, that's class. I just had the terminology. Let me just look at the terminology one more, just for our sake, A-dubs. So CIDR, class. So now we're in class list interdomain routing. So class list interdomain routing. Okay, that's what you'll see the terminology of CIDR. Okay, so that's what we're getting into now. And then again, this is like a great little thingy, I guess, table for us to just keep a mental note on. So when we have our subnets, and we see 255.254.0.0, all right, we can just blast out our calculations on what that's meaning. So pretty much this is full of 1, 2, 3, 4, 5, 6, 7, 8 binary bits, where this is full of 1, 2, 3, 4, 5, 6, 7 and a binary bit. So what's that stating is in this portion, even though we have we'll say the 19, we'll just say for it, no, not the 19, that would be a bad one. So we'll say 10.7.0.0. So somewhere in this second octet, even though there's a 7 there, but somewhere in that second octet, there's some network portion in that bit right there. All right. So this is just class list thinking here. All right. Let's keep it moving, folks. All right. Actually, yeah, I'll keep this up. I'll keep this up for our reference. That's cool. All right. So let's go on to number 4. Working at the help desk. You receive a call and learn a user's PC IP address and mask 10.55.66.7.7 with mask 255.255.255.0. When thinking about class full logic, you determine that the number of networks and subnets and host bits, which of the following is true in this case? Okay, so which is true. So the network itself has, let me see, 255, 255, 255. So there's 24 bits in that network, okay? Oh, wait. Let's think class full. So, all right. So it'll actually be C. It'll be C, and this is why. Because now we gotta undo some of the other stuff. So, all right. Let me just write that down. So 255, 255, 255.0, and then the address is 10.55.66.77. All right. So in CIDR, this would still be, again, because we still have to remember a couple things. So this is still a Class A network. This is still considered a Class A network, okay? So no matter what, network and this will always equal still 8. All right. Subnet though, all right. Subnet will equal, all right, this portion right here, all right, because we're subnetting this portion out of our network. So 55 and 66 are a subnetted portion, all right, and that's equaling 16 bits, all right. And then right here, all right, this is our host. So host will equal 8 bits, all right. So in CIDR, this would be the equation for CIDR. So our network will equal 8, our subnet will equal 16, and our host bits will equal 8. Okay? Again, all in all, this will equal 32 bits. Okay? Because again, this is IPv4, and we can't get past the fact that we have a 32 bits all in all. How many do we have to choose? So what'd you say? E and C? So remember though, we have to which other ones is true? We have to use this equation though, and you are right, A-dubs, all right? But with this equation, what this is going to go over the process is finding the network, finding the subnet part, and then finding the host part, okay? So E would be correct, all right? But in this, I guess, terminology, it will only be actual C, okay? It would be C because we're only dealing with 8 actual host bits on this equation. Yeah, no. You're good. Trust me. This is where it gets a little bit fuzzy. You know what I'm saying? It gets a little bit confusing because you still have to, even though we're not dealing with class full addressing, we still have to keep in mind of the actual class, okay? Since we're still dealing with the class, even though we're not particularly dealing with the actual class, this is where CIDR it can get a little bit wonky on us. But this is why we, reviewing this chapter again, even though as much as I want to just breeze through this chapter, reviewing this chapter again will be beneficial for us to do, What did I say? C. Okay. All right. Working at the help desk, you receive a call and learn a user's PC address is 192.168.9.1.27. When thinking about this using classful logic, you determine the number of network. All right, so let's do that again. All right, so we have 27. So if we come over here, what will equal 27? So we have 2 for 5, 2 for 5. All right, 2 for 5. All right, and then we only need 3 bits, so that'd be 224, 224. All right, because we're only needing 3 bits, because 225, 225, 6, 8, 16, 24, and then 27, giving us 3 more bits, so it'll be 224 right there. Okay, and our address is 192, 168. 168.9.1. All right. So how many binary bits? So remember, there's only 3 more binary bits in this one. So we have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So n. So we got to remember this is a class C. Okay. So this is a class C. So n will equal 24 no matter what. Okay. Now we have a subnet portion of 3. So subnet will equal 3. Okay. And then host will equal 5. Okay. So it'll be n equals 24, subnet equals 3, and then host equals 5. So that's really the equation right there. What up? Oh, I got to know what up, LMath. How we doing? So yes, you are correct. You are correct, LMath. So in this instance, because of the network 192.1.6, because obviously this is a class C network where the network resides in the first 3 octets. Okay. Thank you, man. You're on the cutting edge doing the new stuff with CML 2.1. Yeah, dude, I love Cisco Model Lab. I love it, dude. Honestly, I prefer. I started off, I started off with, I got the bug with GNS3, but obviously to get GNS3 and do it the right way, you have to purchase Cisco Model Lab. So I started off with Cisco Model Lab 2.0 originally. Cisco 2.0, it looked with the blinding white screen and everything else. I was still using GNS3 for just a little while, but then 2.1 dropped, and they made some big changes and they updated some stuff because there was a lot of bugs in 2.0 as well, and I found a whole bunch of those bugs. Then 2.1 came out. 2.1 looks amazing, but there was still some issues with 2.1 in the beginning. And I had to reach out to and I actually dropped the line on some of the DevNet folks and said, hey, listen, here's some of the bugs that I found and whatnot. And they actually went back, and then in November, I think it was on November 28th, that's when 2.1.1 dropped. And yeah, ever since then, man, I've been doing a whole bunch of lab. You can do everything in Cisco Modeling Lab. Everything. I mean, those images that you have in there, those Ubuntu images, you connect that thing to the internet and wham bam, thank you, man. You can make DHCP servers, DNS. You can do anything you can want, you can imagine inside Cisco Modeling Lab. That's why I love using it. I'm just curious, I can't find any questions. Just curious, I can't. If you can't ask, I know it's study time. Can you get your CSR image to work on CML? I know you use the server EXSI, SSH works now though. Can you get your yeah. Let me go over here for you real quick. I'll just boot it up, and as we're talking, we'll go back. I'll boot it up as we're talking, and we'll go back to it after it's done booting up. All right. Here, I'll even throw a. I'll throw that in there. I'll throw that in there for us too as well. All right. So as we're continuing on, once that, we'll give it some time to boot up, and then we'll go back to it. All right, LMath. But again, like I ask everybody, I'll do this for this instance because I love this stuff, man. But like I try to keep everything pertinent to study time. But we'll take a look at the CSR, the cloud server service router, and yeah, I'll take a look at it for you. We'll definitely dive into it, my friend. How are you today, though? Ooh, that went down the wrong way. Woo. Coffee. So much coffee. Yeah, I'm glad they fixed the SSH part of it. The yeah, because I think if you've probably if you've caught some of my stuff before, you've probably seen the issues that I ran into with SSH on the IOSV router image there, and it just aggravated me. And trust me, it's not that I get aggravated. It's just like, these are just like fundamental things that you would want in those images, uh, so you can lab a particular way. That's it. All right, let's move on to question 5. Working at the help desk, you received a call and learned that a user's PCIP address in mass 192. Oh wait, we answered this one. Oof. All right, I'm standing in the way, aren't I? I think I am. It's okay. So that would be, like we said, 24. So that'd be A. All right. All right. Question 6. Which of the following statements is true about a classless IP address concept? Okay. Use a 120-bit? Nope. Applies to only class A, B? Nope. Separates IP address into network, subnet, and host bits? Yes, it does. So 6 would be C. Right? It does not, so it still applies the class A, B, and C rules to it, no matter what. All right. Which of the following masks, when used as the only mask within a class B network, would supply enough subnet bits to support 100 subnets? Okay, so this is when we have to do our math. So we have a class B network, and we want to find how many subnet bits would supply 100 subnets. So that's when we do the 2 to the S. So we got to do the 2 to the S to find out how many binary bits would get us to that. All right. Now that we're talking about a class B network. So remember, a class B network is 2 for 5. Not 2 for 5. Dot 2 for 5. Dot 0 dot 0. By default, class B network is 2 for 5, 2 for 5. All right. So it has already 16 bits in its network. Okay. All right. So now we have to find out how many subnet bits, all right, do we need to get us to 100 subnets, okay? So that's just doing the 2 to the, so let's see, let's do our math here. So that'd be 2 to the, yeah, it's like 2 to the 6th, I think. So it's 2 to the, is it 2 to the 7th? I think it's 2 to the 7th. Apologize for my awful math. So, so 2 to the 7th. So 2 to the 7th. All right, 2 to the 7th would get us 128 subnet bits. Okay. So if we come over here, we go 1, 2, 3, 4. So right here. So we need 254. All right. 254 would allot us 128 subnet bits. All right. Well, it would allot us for 100 subnets. All right. Let's do the 6 then. It's only 64, man. Definitely not D. 16 plus 7.
It's definitely not C either. It's only 4 bits. Choose 2. I mean, A and B would be way more than enough. I'm gonna go with A and B. A and B would definitely be more than enough. Because this is only giving us, that's only giving us 64. Yeah, exactly. Yeah. So I'm gonna go with A and B because again, it's overkill. But yeah, C wouldn't be it, and then D wouldn't be it. Let's see if we're right. Ooh, we are right. All right, let's take a look. So we got C, good. B, good. B, C, A. Oh, I got something wrong on that one. And then let's take a look. So they're saying 6 is D. Which of the following statements is true about classless IP? Separates the IP address into network, subnets, and host specs. Ignores class B network rules. Huh. We'll have to dive into that. But I still figured, all right. All right. So it's saying a classless ignores class A, B, C network rules. But it still, though, applies to it somewhere. All right. We'll just have to review that fact. Yeah. We'll just have to review that fact. All right. Because the reason why I figured C was it does, in some concept it separates network, subnets, and host parts. Doesn't totally ignore class A, B, and C network rules. It still includes, because you still have to include the network part as it would be. Okay. I'll take Waldo Odom's word for it. He's the Jedi Master of all things CCNA. Look at that. Just as I clicked over it, it booted up right then. Woo! It's a working a slow, man. Holy guacamole. What do you name your interface, buddy?
Oh my goodness, it's so slow. Don't know. It's blowing up on me, math. I got I gotta be my hardware running. Gotta be my hardware running my host laptop with 8 gigs, 5 CPUs, only allowing 4 total G's on the VM, and it never gets out of the queue state for me. All right, so what I give CML I give CML, what do I give it? I think is it 8 CPUs? It's like, yeah, I think I give it CML 8 CPUs, and then I give it 16 gigs of RAM. Crash inflow. Oh, so did it crash? Hmm. No, no, I think it crashed too on mine. Whoa, oh, hold on, Betsy. Oh, is it coming back? Freaking out on me. Let's give it a minute, see what happens. She's definitely a hog, though. Yeah, but it's only saying 18 to 17% CPU usage, and memory's only at 22. So I mean, it's not kicking. It's not totally devouring up everything. Huh. Maybe it's not just you. Maybe this thing's just broken. Like I said, there's so many. I mean, just myself. I mean, I found so many issues with this thing. So many issues just with CML. So that's why I tend to use like the iOS V. Uh, I did though. I don't know if you've caught in. Come on, come on, come on, come on, come on, come on, come on. Do something. I don't know if you've caught in one of my earlier streams, LMAP, but I downloaded PFSense. I downloaded PFSense as a VM, and I created a virtual. I created a V switch in my EXXI server, and I did some cool stuff with obviously like adding it to a. I'll have to log back into my server real quick.
to show you. But I use pfSense as a virtual router between my main network and then the vSwitch, that auxiliary network that I created to create a NAT, so I can have, like, because EXSI, it doesn't have like the option like VirtualBox or VM, where you can just select the quick option to have like a NAT bridge. Well, EXXI doesn't have that like built-in option, just because it's EXXI is like it. You're supposed to know already how to do that stuff. Yeah, yeah, it was pretty neat, because I had to like learn how to use pfSense real quick, and I made a D8. I put a couple VMs in it. I put a Fedora and an Ubuntu VM in it, and then I put an Ubuntu desktop and Ubuntu server, and then it's rebooting all over again. Um, Heck yeah, dude! Just messing with VMs and stuff like that, you can learn so much, dude. Ever since I started messing with virtualization technology, I had to. It forces you to learn Linux. You know what I'm saying? You have to like dig your heels in and learn Linux, or you're gonna be lost in the sauce. You know what I'm saying? So I mean, just by messing with virtualization tech, it's like you have to get your Linux knowledge up. Ugh. Heck yeah, man. All right, I'll let that run for like another second. I'll let it run just for a little bit longer to see if it changes its mind and wants to cooperate with us. Um, let me just log into my server real quick. Hold on one second. I'm just gonna log in. I'm back. All right. Yeah, no, you're good. You're good. I just wanted to show you this, I guess while we're talking about it. Um, so, I just wanted to log into my server real quick. So, what I did was over here in EXXI, I created I call it NX group, whatever, you can name it whatever. But what I did is the NX router, that's actually the pfSense. This is a pfSense image right here. And then these are the images that I threw up on here. This is just an Ubuntu server image, Ubuntu server, Fedora server, and the Ubuntu desktop. The reason why the Ubuntu desktop, I put the Ubuntu desktop on here, is that way I can log into the pfSense's web-based GUI, which is really, really nice. I'll do more. I'm gonna do more streams on this particular type topology. You know what I'm saying? This is more like virtualization type topology. This is like, yeah, I guess this would be like more like today's type sense of how like SD-WAN and SD-WAN type topology, software defined wide area network or local area network type stuff. But yeah, this was real neat. And the reason why I built this is because I had a DHCP class and a DNS class, and I didn't, obviously you don't want a DHCP server inside of your own actual main network. You know what I'm saying? Because
it's going to be fighting with your other DHCP server, my at-home router. You know what I'm saying? So I had to figure out. It's like I was like, man, how do I figure out how to do this in EXXI? I could have done it in VMware, you know what I'm saying, like that, but I didn't want to. I wanted to do it for realsies in EXXI. So I figured out how to do it, and it's off. These are off on their own actual. Oh, thank you, man.
So far, I think people come to your videos because of this stuff. Totally watch that whole DHP.
Dude, thank you so much, man. I appreciate that, Elmath, dude. Like, my whole thing is, man, is this thing gonna work? I don't know. I'm on a journey to become CCNA certified, and then once I become CCNA certified, we're gonna be going straight from CCNA to DevNet, and then from DevNet we're gonna be going to CCNP, and then so on and so forth, and eventually I'm gonna be going after my VMware Architect certification as well. I want to take everybody that spends the time with me that's watching these videos. I want them to, if I could spike the interest in somebody, or if I can maybe, explain something in a certain way that wasn't explained to them before, that helps them now, I guess, look at something in a different light. Because again, I'm a physical type person, and I have to physically do things to get them in my, to cram them into my memory bank. And I just hope that comes across, and people can pick something up, man. Pick something up from that, and I appreciate those kind words, man. Thank you so much, Elmatt. Yeah, I don't know if we're gonna have any luck with this CSR image here, brother. I'm gonna continue to let that stew in the background. All right, let's get back to our conversation here. So subnet conversions. This section describes how to convert between different formats for the subnet mask. You can then use the process when you practice. If you already know how to convert from one format to another, go ahead and move to the section practicing converting subnet masks later in this chapter. So three mask format. Subnet mask can be written in a 32 binary bit numbers. But not just any binary bits. In particular, the binary subnet mask follows these rules, okay? Values must not interleave ones and zeros. So that's pretty much stating you cannot mix binary zeros with binary ones, all right? Either it's 1 1 1 1 1 1 1 1 1 0 0 0 0 0 0 0, or it's 1 1 1 1 1 followed by 0 0 0 0. All right, that's it. There's no cross plane. You can't have 1 0 1 0 1. This is a no-no when it comes to subnet mask. Okay, it's either all binary ones, all binary zeros, or as it's going to say, if ones exist, they are in the left portion. All right, and then if zeros exist, they're in the right portion. Okay, so these are the three rules. They're all binary ones. It's all binary ones. It's all binary zeros. It's all binary zeros. If there's a combination of the two, then binary ones will always be on the left. Binary zeros will always be on the right. Those are the three rules to always stick to.
Are we watching this evening? I'm probably going to watch your stuff along the way. Pretty close to taking the cert myself. Cheers.
Dude. Please, when you take the cert, man, come back, dude. Tell me how you did, man. Don't tell me how it, I don't want to know the answers and whatnot. But, dude, I would be so happy to hear back from you after you take the cert. I'm hoping, my hope is by February, the beginning of February, I should be done with part one, with the two books, with the two CCNA books. And by February, I'm hoping to go after the CCNA cert
And then shortly after that, it's gonna be. I'm probably gonna give myself maybe like two or 3 weeks after I do the CCNA cert to go right to the DevNet cert, just because the DevNet cert covers a lot of the fundamental stuff in it as well that the CCNA cert, at least from, because I've already read some of the DevNet Associate book already, and obviously I have an understanding. Thank you, man. Thank you so much. I have an understanding of how to program Python, and if you watch some of my earlier stuff, you can see I already understand Ansible and how to use Ansible, how to manipulate Ansible. My biggest crutch right now is APIs. It's because I haven't spent enough time on understanding and manipulating APIs. That's going to be my only crutch. That's it. Once I get past APIs, I think I'm going to be. I think I think I'm going to be pretty smooth sailing after that. But yeah, that's pretty much it.
I think watch the CBD Nuggets. They're great on Postman.
Yeah, that's what I've heard. So, I mean, if you've already told, I've got a subscription to O'Reilly Media, and all my stuff I do right off O'Reilly Media. I have live courses on Postman. I actually took I actually have it too, because I have the recording of it. I have Weldon Odom went over a whole REST API course and stuff like that. I have to go back and review it and dig into it. I just need to again do what I always do to, slam dunk that fundamental knowledge into my brain here. All right, I'm gonna give this thing. I'm gonna say that this is not gonna work for me. So it's just not you, LMAP. It's me as well, brother. It is not liking me at all. I wonder though. I wonder if we're going about this maybe wrong. I wonder if we need to hook up an exterior connection to this, and if that's the reason why it's not working. I wonder if it has to have some connection. That might be actually it. I think we actually have to have this hooked up to an exterior connection, honestly. Shut you down, buddy. You know what I'm gonna do? I'll go on the CML. I mean, I'm pretty sure you've already been on there, LMouth, but I'll take a look on the actual. Are you do you ever go on or have you gone on David Bumble's Discord? Go on David Bumble if you. I don't know if you're part of David Bumble's Discord.
It does need an external, I believe, through a multi-layer switch.
Yeah. So I think so. I think that's what we should do. Is we'll hook up. I'll have to. What we'll have to do is though we'll have to set up an exterior connection and then have an IOSV set up as a DHCP server. So then once we hook up, yeah. All right, I'll make a topology, because I think if we hook up an external connection with an IOSV image, have that IOSV image set up with a DHCP server, so then once we hook the CSR to it, it'll dynamically address that, and then we can access that through Snap. We can probably access that through one of the actual Alpine Linux images on there, because those Alpine Linux images, they have a web interface, they have a web GUI on there. So maybe we can do that. All right, I'll think about how to set that up, how to set that lab up, LMAT. Yeah, definitely. I'll definitely think about how to set that lab up, and we'll get to that. All right. So here we go. So we're back here. Again, we're just talking about the rules of subnet masking. Okay. Obviously, it's stating you cannot interleave ones and zeros in a subnet mask. Okay. Remember the rules: either all binary ones, all binary zeros. Okay. Or if you have ones and zeros, all the ones off to the left, all the zeros off to the right. There's no interleaving of the binary bitsies. Okay. The two alternative dotted decimal notation. All right, converts each set of 8 binary bits to the decimal equivalent. So 1, 2, 3, 4, 5, 6, 7, 8 equals 8 in dotted decimal notation, so on and so forth. All right. And then obviously you have, so the dotted decimal notation. All right. That's just counting the binary bits, not what it equals in binary. So 1, 2, 3, 4, 5, 6, 7, 8 dotted decimal notation. All right, it's equaling the binary bits. Okay, it's not equaling what it equals in binary. So binary 1, 2, 3, 4, 5, 6, 7, 8, 8 binary ones again would equal 255. Okay, all right. So dotted decimal, it's just counting the bits. Binary, obviously, what it equals in actual binary. Okay. All right. Continue on here. Again, I'm going to try to not breeze through these chapters, but just touch on the parts that we need to touch on. All right. Just because I don't want to spend too much time here, because we should have already been into part 5 by now. So note that although the terms prefix or prefix mask can be used, the term CIDR mask or / mask can also be used. This newer prefix style mask was created around the same time as the classless interdomain routing. We'll say that again, classless interdomain routing, CIDR. Specifications back in the early 90s, and the acronym CIDR grew to be used for anything related to CIDR, including prefix style masks. In addition to the term / mask is sometimes used because of the value, including the slash. All right. You need to be comfortable working with mask in the different formats. The rest of this section examines how to convert between the 3 formats. All right, converting between binary and prefix. All right. Converting between binary and prefix mask should be relatively intuitive. After you know that the prefix value is simply the number of binaries ones in the binary mask. For the sake of completeness, the process to convert in these sections are binary to prefix, count the number of binary ones in the binary mask, write down the total, boom, there you go. Prefix to binary, write the P binary ones, where the P is the prefix value followed by the binary zeros as required to create the 32-bit. So again, this is just going over exactly what we've already talked about, just counting those binary ones. All right, and it keeps going. Yep. Okay. All right, converting between binary and dotted decimal notation. By definition, a dotted decimal notation DDR using the IPv4 addressing contains 4 decimal numbers separated by a dot. Each decimal notation represents 8 bits. So a single dotted decimal notation shows 4 decimal numbers that together represent some 32-bit number. Conversely, the dotted decimal notation mask and the binary equivalent is relatively simple to describe, but can be laborious to perform. All right, cool. Oh, you gotta don't put the space. A-dubs, don't put the space. So do exclamation point my weather, no space. There you go. Woo 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 woo.
What is it in Honolulu today? Ooh, that's nice. 80 degrees.
Oh, dude, that is perfect weather right there. Perfect weather.
I think it's actually kind of warm where I'm at right now. Let me see. What is it in Cumberland? It's 41. It's not bad. Oh, it's raining right now. Wherever that's getting its information from is wrong. Then
It's a crisp 41 degrees out where I'm at. It's not too bad though today. I'll take 41 over 5 degrees. Right? Exactly. It's actually not too bad. 41's not too bad. At least over here, it's not too bad. All right. All right. However, the conversion, do the decimal binary conversion, but practice your decimal binary conversions to get faster. If you choose this path, consider the all right. So there's like some Cisco binary game, which you could find at Cisco Learn HTTP ://learnnetwork.cisco.com. That'd be a cool little thing. We won't do that right now. There's a binary conversion. Cool. So this is just going over that table. Here's that table again. So 0, 128, 192, 224, 240, 248, 252, 254, and 245. All right. So again, this would be a good one to remember, just to keep in our heads. It'll just help us, it'll help us just get faster at how we're memorizing these important numbers that, will just make our lives a little bit easier and faster. We'll just get faster. How's that? All right. Yep. Binary to decimal. Binary to decimal. Organize the bits into 4 straight, 4 sets of 8, each octet value. Yep. Again, it's just going over, just reiterating what we've already touched on. If you guys want me to slow down on this, just tell me to slow down and I'll explain it. But again, I think we've hammered this. This logic down pretty well. So I mean, if you just go in there, that table is 2 binary 1s followed by 6 binary 0s, giving you the 245.192 subnet mask range. Okay. Not scrolling too fast. Same thing here. So we have 255.240. So again, if we go to our little chart, 240, that's 4 binary 1s followed by 4 binary 0s. Obviously giving us that slash, what is that? Slash 24, 25, 26, 27, 28, slash 28, dotted decimal, slash mask, subnet mask there. So it's just going into more of the same stuff that we've been already talking about, converting between slash notation, decimal, and binary. Okay. Practice. Practice makes it perfect. All right. Let's touch on this real quick. All right. Identifying subnet design choices using masks. Subnet masks have many purposes. In fact, if 10 experienced network engineers were independently asked, what is the purpose of a subnet mask, the engineers would likely give a variety of true answers. the subnet mask plays several roles. This chapter focuses on one particular use of the subnet mask, defining the prefix part of the IP address in the subnet. The prefix part must be the same value for all addresses in a subnet. In fact, a single subnet can be defined as an IPv4 address that have the same value in the prefix part in the IPv4 address. While the previous paragraphs might sound a bit formal, the idea is relatively basic. As shown in this figure, the figure shows that the network diagram focuses on two subnets: a subnet of all addresses that begin with 172.16.2, and all of the subnets made of all addresses that begin with 172.116.3. In this example, the prefix, the part that has the same value in all the address is the subnet is the first 3 octets. Yes. Yep. Yep. Cool. While people can sit around at a conference table and talk about how a prefix is the 3 octets long, computer communicate that same concept using subnet mask. In this case, the subnet uses mask/24, which means that the prefix part of the address is 24 bits long, the first 3 octets. Yep. The section explains more about how to use subnet mask to understand the concept of a prefix part of the IPv4 address, along with these other uses for subnet mask. Note that this section discusses the first 5 items in the list. All right. Define the size of the prefix part of the address in the subnet. Define the size of the host part in the address in the subnet. Can be calculated numbers of hosts in the subnet. Provide means for the network design to communicate the design details, the number of subnets and host bits to the device in the network. All right. Under certain assumptions, can be used to calculate the number of subnets in either classful network. All right. Can be used in binary calculations on both the subnet ID and the subnet broadcast address. Okay. All right. Masks that define subnet addresses into 2 parts. The subnet mask subdivides the IP address into subnets into 2 parts: the prefix or the subnet part and the host part. The prefix part identifies the address that resides in the same part of the subnet because all IP addresses in the same subnet have the same value in the prefix part of their addresses. The idea is much like the postal code. Yep. So again, it's just stating the same things that we've talked about, that we just keep reiterating. Okay. The prefix subnet part equals in all addresses in the same subnet. So the prefix, so when it says prefix, we got to think prefix as network. All right. And this content, the prefix and the network, those 2 terms are we can look at as the same. So the network part, prefix part, the same. Okay. That will always, so that part of the address, the network or the prefix part, will always be consistent within that actual network. Okay. The host part, that's what changes. Okay. Host part's different, all the address in the same subnet. All right. For example, in a subnet that in concept includes all addresses whose first 3 octets are 10.1.1. Okay. So the following list shows you several addresses in that. So it has 10.1.1, 10.1.1.2, 10.1.1.3. Okay. But the 10.1.1 is the prefix part that remains the same. All right. The host part is what will continue to change. Okay. All right. So here we go. So it's just stating over the prefix and the host part. All right. Again, prefix part is what the subnet mask is what is determining that prefix part, the network part. So because all those binary ones are what tells the computer this is the prefix part. This is the network part of this address. Okay. That's what that mask is representing to that computer. So when the computer sees this information, it says, okay, we have 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, we have 24 ones and 8 zeros. Okay, so the first part of this IPv4 address, the first 3 octets, is all the prefix part, the network part. All right. The last octet, that's the host part. All right. Mask and class divided addresses into 3 parts. Okay. And so this is where I was coming up with that that earlier mentality, that earlier thinking, where CIDR still has it still applies some rules of class full IP addressing. Now let's discuss that, because this is the part I actually wanted to get to in this chapter, and that's why I was just waiting to actually get to this part. In addition to the 2-part view of the IPv4 address, you can also think about IPv4 addresses of having 3 parts. All right, 3 parts. To do so, just apply class A, B, and C rules to the address format to define the network part at the beginning of the address. This added logic divides the prefix part into 2 parts, the network part and the subnet part. And that's where I was coming up with that mentality of still maintaining the rules of class A, B, and C. Okay, where if we had a 10 dot whatever network, that first octet in that 10 dot network, that would be the network portion. Anything between that would be subnet portion, and then obviously whatever else would be the host portion. That's where we come up with the N equals network, S equals subnet, and then host equals SSH equals host. So that's where I was coming up with that equation right here. All right. So again, there it is right there, and this is where again I was coming up with that mentality. All right, class lists and class full addressing. Okay, this is the part I wanted to talk. The term class list addressing and class full addressing refers to 2 different ways to think about IPv4 addressing as described so far in this chapter. Class full addressing means that you think about class A, B, and C rules. So the prefix is separated into the network and subnet parts as shown in the figure. Class list addressing means that you ignore the class A, B, and C rules and treat all right, so that's where I got that one wrong. So class list totally ignores the rules for a class full. And I kind of knew that, but I thought though it still considered the A, B, and C rule in its logic, but I guess it doesn't. So that's where I guess, I just had to read it to make it true to me. All right. They treat the prefix part as one part as shown and the host part as the other part. Okay, cool. Class list addressing, the concept that the IPv4 address has 2 parts, the prefix part plus the host part, as defined by the mask, with no consideration to A, B, or C rules. Class full addressing, the concept that an IPv4 address has 3 parts, network, subnet, and host part, defined by the mask and so defined by the mask and the class A, B, and C rules. Okay, all right. Unfortunately, the networking world uses these terms class list and class full in a couple different ways. In addition to class list and class full addressing described here, each routing protocol can categorize as either a class list routing protocol or a class full routing protocol. In other uses, the term class list routing and class full routing refers to the same details of how a Cisco router forwards and routes packets using the default route in some cases. As a result, these terms can be easily confused and misused. So when you see the words class list and class full, be careful to note the context, addressing, routing, or routing protocols. Okay. All right. After you know how to break the addressings down to class list, class full rules, you can easily calculate a couple different important facts about the same basic math formulas. First, for any subnet, after you know the number of host bits, you can calculate the number of IP addresses in that subnet. Next, If you know the number of subnet bits using class full addressing concept, and you know that only one subnet mask is used throughout the network, you can also calculate the number of subnets in that network. The formula just requires that you know the powers of 2. So knowing the powers of 2, everything goes up by the powers of 2. That's because obviously you can have, binary works with either on or off, powers of 2. Okay. All right. Host in a subnet is again that formula 2h minus 2, because remember we got a minus 2 for the subnet for the network ID and the network broadcast address. Okay, so 2 to the h minus 2, you're minusing 2 for the network ID and the broadcast address. Okay, subnets in a network, that's 2 to the s. Okay, where s is the number of subnet bits. Only use this formula if only one mask is used throughout the network. Okay. All right. The size of the part of the IPv4 address can be calculated. The math is basic, but the concepts are important. Keep in mind that the IPv4 address are 32 bits long. 2 parts of the class's addressing must be added up to 32. Cool. Yep. All right. Doing convert the masks. Yep. All right, so we've kicked that chapter's butt then, guys. All right, some just in key terms: binary mask, dotted decimal notation, DDN, decimal mask, prefix mask, CIDR mask, classful address, and classless address. All right. And it's just giving us a couple tables and just some problems. All right. Let's go on to chapter 14 now. All right, we're making good headway. I'm gonna just go grab. I'm gonna run to the bathroom again real quick, guys, and grab another drink real quick. I'll be right back, guys. Just give me 2 seconds. Promise. We're back, baby. Gotta grab a drink real quick. It's not a beer, trust me. It's seltzer water. All right. Let's continue on. And again, we are making good headway today. Where's me mouse? Me mouse, come back, me mouse. All right, guys. Nope. Okay. All right. All right. Let us continue on here. Okay. Analyzing exiting subnets. All right. Configure an IPv4 address, addressing, and subnet. Often the network task begins with discovering IP address and mask used by some host. Then to understand how the internetwork routes the packets to the host, you must find key pieces of information about the subnet, specifically the following: subnet ID, subnet broadcast address, subnet range of usable unicast IP addresses. This chapter discusses the concept and math to take a known IP address and mask and then fully describe a subnet by finding the values in the list. This specific task might be the most important IP skill in the entire IP addressing and subnetting topics in this book. These tasks might be the most commonly used tasks while operating and troubleshoot networks. Okay. All right. Question 1. When you think about an IP address using a classical addressing rule, an address can have three parts: network, subnet, host. If you examine all of the addressings in one subnet in binary, which of the following answers correctly state which of the three parts of the address will be equal among all addresses? It is the network part. It's the network part. Choose the best answer. Which of the class full addressing? So we're thinking about class full addressing. Three parts. Which of the following answers correctly states which of the three parts of the address will be equal among all addresses? I'll go with D on this one. Equal among all addresses. Whatever, I'll go with A. The network part never changes. The network part never changes. Alright. Subnet part can change. Alright. Which of the following statements are true regarding the binary subnet ID, subnet broadcast address, and the host IP address values in any single subnet? Which of the following statements are true regarding the binary subnet ID, subnet broadcast address, and the host IP address value in any single subnet? The host part of the broadcast address is all binary zeros, which is true. Yep. Host part of the subnet ID, the host part of the subnet ID is all binary zeros. The host part of the usable IP addresses can have no. The host part of the usable IP addresses must not. No. All right. So it's between A and B here. The host part of the broadcast. The host part of the broadcast address is all binary. Host part of the subnet. The host part of the subnet ID. I know it's B for sure. Let's look for two answers. Host part of the. It's just the way it wording everything here. The host part of the usable IP address is no. Host part of any usable IP address must not be all. Alright, so I'm just gonna go with A and B then. On that one. All right, which of the following is the resident subnet ID for IP address 10.7.99.133/24? Which of the following is the resident subnet ID? So that's 7.9. So that's 7.99. Yeah, so it's C. Which of the following is the resident subnet ID for the IP address 192.168.40.44.30? So let's just do a little bit of quick math real fast. We'll get this done. So what do we got? 255, 255, 2, is it 252, right? Yeah, it's 252. Yeah. 252. 252. Yeah, 252. So all we do is 192, 168, 44, 97. Again, 256 minus 252 goes in increments of 4. So 0, 4, all the way to 97. So 97 divided by 4, 24. 24 times 4 is 96. Should be that. So 96. And then 100. So 192, 168, 44, 96. And then 192, 168, 44, 99. So it's C. Okay, which of the following is the subnet broadcast address for the subnet in which IP subnet broadcast address? Which of the following is the subnet broadcast address for the subnet in which the IP? So, okay, let's do the math real quick. Okay, so we have 27, so that's 2 for 5, 2 for 5, 2 for 5. And what do we got? It's 240, right? 240? 240? Yeah. 224. 224. Yeah. 224. 224. Okay. And then we have 172, 31, 77, 201. All right. So we do 256 minus 224, 232. So this goes up by 32s. 201 divided by 32 equals 6. 6 times 32 equals 192. 192. Okay. So be minus that, so 223, so 172.3177, 223. That would be the broadcast address for that. So it'd be C. All right. A fellow engineer tells you to configure a DHCP server to lease the last 100 usable IP addresses in the subnet 10.1.4.0/23. Which of the following IP addresses could be leased as a result of your new configuration? Okay, let's figure it out real quick. So what do we got? /23. So we have 2 for 5. Dot 2 for 5. Dot That's 254, right? 254? Yep. That's 23. Yep, 254. 54.0. And what's our address? Is 10.140. Okay. Yep. So let's just find out our information here. So what do we got? So 256 minus 254. Obviously it's 2. So we have 0, 2, 4. Okay. So this is the subnet ID. And then the next possible one, 2, 4, 6 minus 5 would be 5. So the subnet broadcast is 10, 1, 10, 1, 10, 1, 5, 2 for 5. All right. So our last, erase that real quick. So we have a range from 10.1.4.1 to 10.1.5.254 range. So that's our whole entire range right there. So we have a pretty sizely range here. All right. Which of the following IP addresses could be leased as a result of the new addresses? So how many does it want me to pick? The last 100. Oh, so it wants the last 100. So if it's the last 100, then it would be 10.1.5, 254 to 10.1.5. Yeah, it'd be 154. So that would be, all right, so it would be C. It'd be C. I see what it kind of funky question, but I see what it was going for. Okay. C. All right. See how we did. Ooh, I got one wrong. One wrong. Oops, 2 wrong. Right, and right. All right, let me see what I got wrong. So this saying D, saying B and D, and D. Let's see what I did wrong. Yeah, so okay. I kind of had a feeling it was on question 1 it was going to be D. And what did I get wrong? So I chose A and B on 2, and it's B, and D. The host part of a usable IP address must not be all binary ones. The host part, any usable IP address must not be all binary zeros. How does that make any sense? The host part of an IP address is all binary zeros. Yes, the host part of any usable IP address must not. Oh, okay. I see what that's saying. The host part of any usable IP address. I see what that states. Man, I swear these questions sometimes they make you like, yeah. The way they word some of these things, man, it's like they want to catch you. It's fine. I get that. So what's that stating is 10.1.4.0 is not a usable IP address because that defines the network ID. All right, so that's what it's stating, that an IP address cannot have all zeros. So this is an unusable IP address, okay? So If it had a 1, that's a usable IP address. Because it has a 0, it is not an actual usable IP address. All right, it's a network ID. That's what that question was gearing my mind towards, and that's what I got wrong. Other than that, we did everything else right. All right, I'm happy with that. All right, where's my board? Okay, let's continue on here. All right. Defining a subnet. An IP subnet is a subset of a classful network created by choice of some network engineer. However, the engineer could not pick just any arbitrary set of addresses. Instead, the engineer must follow certain rules, such as the following. All right. The subnet contains a set of consecutive numbers. The subnet holds the 2H. All right. So remember 2H. All right. Number where the H is the number of host bits defined by the subnet mask. Two special subnet numbers. Two special numbers in the range cannot be used in the IP. So again, that's the lowest. Okay. The most lowest is defined by the subnet ID, and the highest is defined by the subnet broadcast address in that IP4 address range. Okay. The remaining addresses whose values sit between the subnet ID and the subnet broadcast address are used as unicast IP address. So unicast meaning one. Okay, not multicast meaning multiple. Unicast meaning one. All right, una. All right, the section reviews and expands on the basic concepts of subnet ID, subnet broadcast address, and range of IP addresses in a subnet. All right. As an example, with network 172.16.0.0 and 4 subnets. Imagine that you work at a customer support center where you receive all initial calls from users who have problems with the computers. You coach the user through finding her IP address and mask, 172.16.150.441, with the mask of 255.255.192.0. One of the first and most common tasks you will do based on that information is to find the subnet ID and the subnet in which that address resides. In fact, this subnet ID is sometimes called the resident subnet, based on the IP address exists or resides in that subnet. Cool. All right, before getting into the math, examining the mask 255.255.192 or in the classful network 172.16.0.0 for a moment. From the mask, based on what you have learned in chapter 13, analyzing subnet masks, you can find the structure of the address in the subnet, including the number of host and subnet bits. That analyze tells you that two subnet bits exist, meaning that there should be 4 2 to the second subnets shown in the figure. All right. Yep. All right. This chapter, like the other ones, assume. Yeah. All right. Rest of the chapter takes on discovering the details on. All right, the rest of this chapter focuses on how to take one IP address and mask to discover details about that one subnet in which the IP address, resides. In other words, you'll see how to find the resident subnet of the IP address, again using the IP address 172.168.150.51 with the mask of 255.255.192.0. As an example, show the resident subnet as long as with the subnet ID and the subnet broadcast address in the bracket. So it's just showing us a depiction of the range. So it's just subnet ID, subnet broadcast, subnet ID, subnet broadcast, and where does that address fall into that whole entire picture there. All right. Again, I am not skipping. If you guys need me to cover anything, just speak up, guys. But I'm just gonna kind of breeze through this chapter just because, for the most part, we've really beat this up a lot. All right, I'm just looking for key points that just to nail to my I'm just looking for key terms to really just the terminology on that I might get hung up on the actual exam. That's what I'm looking for. Like you saw, I got I think like 2 questions wrong. Again, just because maybe the terminology that I might not just be understanding properly. But other than that, I understand the full entire concept of subnetting and addressing and how to find the first and last addresses here. Ranges of usable addresses, the engineer implementing. So again, this was something that I did wrong on that maybe we should jump into that lab so you guys can kind of see what I did wrong, and then how we can go about how we went about fixing it and whatnot. Is my server gonna just shut down? Whatever, you can shut down if you want. All right, so let's just read this one part.
Yeah, point-to-point /30 is kind of different, but
yeah. So what I kind of just said was and over the weekend on Saturday I built like a quick lab before I had to go to work, and I'll show you it too. I have it still on CML. I was trying to be wicked conservative about how I was doing my IP, my subnetting and whatnot. I was only giving point-to-point links. A range. The subnet mask of 255.255.254, so it would only have 2 actual IP addresses on that point-to-point link. But then when I went ahead and implemented I created a DHCP server on that router. I don't know where I was thinking. I was just kind of like trying to rush through the lab, and I gave all the addressing to the areas in here. Maybe we should just get into that now. Yeah. Let me wipe this real quick though. I don't need that. So this was the lab. This was the lab yesterday that I had ran. And here, let's just boot it up. Let's just get it. I'll get it started. That way we can kind of talk about it. No, I had when I created the pool for the areas. So in this edge router here, I wanted it to allocate addresses to the outside to the local here, and then also to the inside of the local. Same thing on both areas. So this router was going to do DHCP for this area, and then also for this area. What I did was when I did all my subnetting and all the sub interfaces on this router, I gave it the subnet mask of 254. Obviously, that only gives me 2 IP addresses in the range. Fine and dandy. All right, which would have worked perfectly, okay, but when I created the pool, and you'll see the pool, I gave the pool the wrong subnet mask. Instead of giving it to 254 for just these two links here, I gave it the address of 24 255.255.0. So when I was trying to, and it was crazy because DHCP still worked. These still got addressed. All right, they got dynamically addressed by the DHCP server on this, but OSPF wouldn't make an adjacency. And I was like, why isn't OSPF making an adjacency? Like, because OSPF wouldn't make an adjacency, these 2 areas in the inside on the local inside area, they couldn't get addresses. They couldn't obviously speak to each other. And I was going back and forth. I'm like, why isn't this not working? So obviously I had to rush to work real quick. Yeah. So I had to rush and I had to shut it all down. But then while I was working, I was scratching my head, and then it just like dawned on me like the light, and I was like, dummy, because I'm like, because you did one of two things wrong. I'm like, you gave the sub interfaces, a different subnet mask than you actually allocated the DHCP server to give to these local outside interfaces. Here, let me just. This shouldn't be too much. Let's just boot these all up. I'll wait. I'll give this once this boots up. I'll get the switch. I'll get the switch up. The switch is kind of like a beast. It just sucks up so much usage. Yeah, OSPF is awesome, dude. I love messing around with OSPF. Keith Baker's amazing, dude. He's another one. Just like I just love his personality. Keith Baker has an amazing personality. Such a upbeat dude, man. He's so good. He is so good. He's one of those really just knowledgeable guys. I'm gonna scoot over to my my get over here now. And once we get to messing on the command line, I got a zoomed in image that you'll be able to see. Yeah. So I mean, some of the there's a couple guys. There's a couple guys: David Bumble, Keith Baker, and Weldon Odom. Those three individuals right there. Those are my go-to guys. That I I know there's so many other more guys out there, but I tend to just stick to those three fine gentlemen right there, just because their knowledge and the way they teach their knowledge, is tried and true from years and years of experience. Okay, there's a couple other guys out there that they're super, they're knowledgeable and whatnot. I don't know, something about them just rubs me the wrong way a little bit. Joseph Caffarelli. Exactly. That crazy Joseph Caffarelli. Oh, Kevin Wallace, yeah. Kevin Wallace is I forgot to mention Kevin Wallace. Kevin Wallace, again, him and Weldon Odom are like the Cisco CCNA. I mean, so isn't David Bumble and all those guys, man. Kevin Wallace, he's a funny guy though. He's like man, he's like the instructor. He's just got so much material, Kevin Wallace. He does a lot of like live stuff, and his training is like it's funny because his training is a little bit different than everybody else's. Kevin Wallace's. I've taken classes. I've taken live classes. David Bombell's motivation is amazing, dude. I swear, I love David Bumble. I love him. He was the dude that turned me on to he was the guy that got me interested in all this stuff, man. If it wasn't for David Bumble, dude, I wouldn't be into all this right now. So I owe a lot. I owe a heck of a lot to David Bumble, man. I tell you, that dude, he's an amazing person, just in general. I mean, an amazing motivator, an amazing speaker. I mean, David Bumble's something else. And he's so
I don't know how he's like I don't know how he does it, man. He just spits out content left and right. Because I mean, I follow him on LinkedIn. I got him all, you know, on YouTube. I'm on his Discord. Uh, he hasn't done anything on Twitch yet, but you know, he'll do something soon on. I don't know. That's up to him. He already does so many other things, but his motivational comments that he spits out, dude. I mean, yeah, he's an amazing person. Uh, I love David Bumble. All right, so let's get over to here. How's that look? It looks good. I shouldn't have to move it. All right, it's showing up pretty good. All right, if you guys need me, yeah, David Bumble's been around. Yeah, exactly. He's been around forever, ever. But again, I only got turned on to this stuff just this year. So let's get into it. Just want to see how this looks. Thank you. If it's not showing everything, just tell me, and I can manipulate it to you know, obviously I can make it a little bit more zoomed in or whatnot. Every time I change my scenes, I gotta redo all my scenes all over again. So yeah. Look at that. We're already making adjacencies. Woo! The Switch isn't even loaded up yet, but we've already made it our adjacencies right here. Sweet. All right. So again, the problem started here. The problem started here for me. As you could tell, when I made my first DHCP pool, I gave it the subnet ID of 255.255.255.0, which would be fine. All right, this would be fine. But what I had done though, what I had done in my, and again, here's the other pool. So this area, so that's something. Oh, so I have four pools in here. So these two VLAN pools right here. Thank you, man. I appreciate it. I tell you what, doing these streams like this, I have increased my knowledge. It's just like my memorization of my knowledge, just because I'm pushing myself. I'm pushing myself to really know this stuff, because I don't want. It's like I don't want you guys to think I don't want to come off like an expert, because I'm not. But I don't want to look like a complete fool when I'm doing this stuff. So it's like I am pushing myself to really get this stuff down, so you guys can see the progression in the knowledge. You know what I'm saying? So these streams, I'm telling you, it's working out for me. That it's like totally brought it's brought me to the complete understanding of how everything's coming together. Yeah, exactly. It's really making it stick. So again, so these DHCP pools, these right here are for these interfaces. Okay, so for the like the local, I'm gonna call it the local outside. Okay, for these areas. So for the area 1, the local outside interface would be for VLAN 10 and VLAN 20. So this would be, and this switch right here, there's no IP addressing. It's not doing any routing, no nothing like that. All it's doing is just has, and I'll show you, it just has VLANs in it. I have VLAN 1 just acting as the trunk port, and then VLAN 10 and VLAN 20 is just ACK6 ports. Okay, all right. So
again, so these are the two VLAN pools, all right? And then these other pools right here, even though this OSPF adjacency kind of messed that up, these pools are for these areas. These switches, don't mind these two switches. These are just the unmanaged switches. They're like hubs. You know what I'm saying? I just use them because it so it doesn't eat up so much of my Right. I mean, A Dubs, if that comes down the road, I would love, you know what I'm saying? I would love to maybe someday in the future, maybe get hooked up with, I don't know, CBT nuggets or whatever else may be, to possibly do some training courses like this, some paid training courses like this. But my whole thing is I want to share. I will always share this knowledge for free because of just taking what David Bumble has done in himself. Okay, I'll take David Bumble for instance because yes, David Bumble has paid content, and I've bought in his courses off Udemy, and I've bought in his GNS3 course and stuff like that. I've paid for his content, but the thing is he also has so much free content out there for everybody to just get interested in this stuff. And again, that's something that because of what he did for me, I'm hopefully in the future or right now, that's hopefully I get across to. So again, these two network pools right here. Again, this switch is performing DHCP for this area, for this section, and then obviously for this area. All right. Come down here again. All right, now let's get into the sub interfaces now. And this is where I started. This is where I made. I guess I would have to say my first my only mistake is how I addressed the pool. Now, if I had addressed the pool correctly, just on these areas, everything would have worked fine. And what we can do is we can redo that. Okay, we can redo that pool and then make the pool correct. All right. But these sub interfaces. So yeah. So my first actual interface going here. We'll redo it live most definitely. So the first interface is going here again 254 whatever. Then my first sub interface. So my first sub interface, that's just for the native VLAN 1 on the distro on the switch here. That's just because you need when you're making the sub interfaces to a switch to trunk routing, to trunk DHCP information. Make sure we can see the lab a little bit too, as well as the important part of the console, if possible. Yeah, dude. I mean, is this? If this is, can you still see? I just want to make sure if you guys can still see the command line when I switch over to this view. If you could still see, let me do this then.
All right. Give me a good a green light on how that looks now. Let me just I'll zoom this just a tinge bit. That way you can still see you can still kind of see the left. Yeah, you can still see the area. That good now? Thank you very much for that, Elmath. Cool. All right. All right. We'll continue forward then. All right. So let's do this then. Let us go back to the all right. Let's go back to the sub interfaces, and what we'll do is we'll redo that what we did, and then we'll go back to the DHCP pool on the two VLANs, and then we'll do that. All right. All right. Good. So, there we go. What is that? 0 dash. Yep. Okay. 0 dash 1.1. Not in the right mode. Goodbye, adjacency. All right. We're going to get that adjacency right back. So it can't be greater than 30. Yeah, that's one thing I didn't. That's new. Okay, that's fine. Now let's do this then. All right, so we'll have to just go back to those interfaces then and do that one more time, which is fine. We got this. All right. So, yeah, no problem, man. So, what what I just did, sorry about that. I was going probably a little too fast. So, what I did is um we got a message when we went to the DHCP. Let me go back to where I went to DHCP. So, when we went to DHCP, we got a message that we can't make a mask with the /30 notation. So it wouldn't allow me to give that 254 network, okay? That's fine. So what it's pretty much stating is we just needed a network that allowed just, I guess, a little bit more of a range for that network range. So we, instead of giving it 254, I went ahead and gave it the 252. So now we have a DHCP pool for those two networks now in the 252. Okay, which then it gives me 4 addresses. So we have 4 addresses now that we're using instead of wasting 255 addresses. We're only going to be wasting pretty much 2 addresses. I can live with wasting 2 addresses, okay? So instead of having the 254 on those sub interfaces now, I just had to go, and then subsequently, I had to just go back again into those sub interfaces and then reconfigure those with that same actual subnet mask on that. So let's just run let's look at our configuration real quick, and then we'll go into the other routers, and then we'll shut down those interfaces, and then we'll bring it back up, and they should get a all right. So cool, look at that. So our VLANs now, so we have VLAN 10 VLAN 20. Again, I'll show you in the switch where that is. So area 1, so that's going to be on the local outside on this one. So VLAN 10, VLAN 20. We have it in the
I didn't even notice the router on the sub interface stuff at first.
I love the router on a stick. The router on the stick is my most favorite thing in the world, my friend. I've so the router on the stick used to be, it was like elusive to me at first on how to do it correctly. And then I was like, man, I'm gonna dive my heels deep into doing the router on the stick perfectly. So now I've got the router on the stick topology nailed to a T with trunking and encapsulating within a switch. You know, and I can, you know, as you can see, we're going to be able to use DHCP throughout the whole network just off of this one router here. All right. And this is a managed switch. So this is a layer 3 switch, but I'm using it as a layer. I'm using it just as a layer 2 switch. I don't have it doing anything with IP addressing or nothing like that. Yep. That's it. Cool. Cool. You know it. All right, so that's good. All right, let's just take a look at our interfaces. Want to make sure that they're addressed right. This one is still fine because that's just going to the trunk. Perfect. So we should be good now. Let's do that. Let's come over to this one now. I'm going to give it the shutdown command. And then the no shutdown. So hopefully, yep. And then once we bring it back up, we should get I didn't exclude any addresses from that range, did I? No. Yeah, look at that. So we just got our new IP address. All right, 10.10.10.110.2 and the correct subnet mask, and right away, and boom, right away, we just made our adjacency. Boom, baby! Touchdown! All right. And then what I'll do, haha, exactly. So again, we'll come right over to this router now. And let's go into that interface. We give it 0-0. Let's give it the shutdown command. And what I want to show you real quick is, I just want you to see the configuration on this area router real quick. So when I boot up these area PCs, you could see that I don't have any DHCP configured on this router at all. So that interface, I just have it being addressed dynamically by DHCP, which is on that router right there. And then I statically addressed just this inside interface, okay, because of how I set up the DHCP for that area. So if we go back to the area 1, so the default router, I have that, so that I have statically addressed to the interfaces on the local inside of both routers, okay? But again, as you can tell, I just have that one static address, and that's, and then obviously OSPF, and then that's it. So when we come over here, let's go back onto this one. All right, so you're shut down now. Let's give you the no shut. Let's bring you back up. And then it should, I mean, that was pretty fast on that other one. We should get our addresses, and we should make our adjacency almost instantaneously. Let's see it. Woo, baby! That's the other one. So look at that right away. So we got our address in the 1.120.120.2. That's the address in the correct subnet mask. And then right as that DHCP did its thing, OSPF made its adjacency right then. All right. So if we do a do show IP route, we should have all of our OSPF routes in here. So look at that. So we have our OSPF, all of our routes learned by OSPF. Beautiful. All right, now let's come over here. Get these guys fired up. Fire it up. Oh. There you go. Look at that. So there's some of our information right there. We've made our adjacencies. All right. Off of our sub interfaces. Yeah, so again, so when I first made this lab, the sub interfaces I had on the subnet mask of 254, okay? But when I created the pools for those local outside interfaces, I like brain farted. I must have had like a seizure or a stroke real quick, and I totally forgot everything of my everything that I've learned so far, and I gave it the subnet mask of 24. Totally brain farted on it, and it's funny because DHCP still allocated an address, so they still the interfaces still got addressed, but OSPF just would not. It wouldn't make an adjacency. I was like, what's going on? What's going on? Then I had to think about what I actually did wrong. And obviously, I just, the most simplest thing, the most fundamental of things. Yeah, and because I put it in the wrong subnet, totally different subnet. Yep. And it was actually, it was a good thing that I guess it was a good thing that I did that. It was good that it didn't work. How's that? Because it gave me then the opportunity to, again, I love, to go back and troubleshoot what went wrong. You know what I'm saying? I have a topology that should work. Why isn't it working? Well, let's now figure out why isn't it working. Let's come up with why. Exactly, A-dubs, exactly. You learn the most when you make mistakes. And because then it's like, it was like, for instance, it's like getting one of David Bumbles' packet tracer labs, and you know how he'll give you a lab and he'll say, what's wrong with this topology? Give me 3 or 4 things that are broken in this topology and figure it out yourself. And that was like a similar, for instance, case that I did to myself without even knowing it. I had a topology that should have worked. Why isn't it working? So then I had to, again, even though it was such a simple thing that I put the wrong, I put the wrong address in DHCP, it took me just a couple minutes to just go back and figure out why. Oh, because I was blaming OSPF at first. I was like, did I mess up on my wildcard addressing? You know what I'm saying? Because wildcard is it's backwards than subnetting. You know what I'm saying? You have to think about wildcard addressing differently than you think about subnet addressing. So I'm like, did I mess up how I address the wildcard on the OSPF? Did I put it in the right area? You know what I'm saying? I usually put everything in area 0. Did I mistakenly put it in area 1 for some reason? So it took me, it took me back a minute. But again, it was good. It was a great use case to it. These should, yep, they have they're addressed. All right, and these are all addressed to the did you see where Network Chuck and Calvin messed up a DHCP server lab for trying to fix that one and going back and to watch how to actually fix it? Basically taught me most via troubleshooting. Yep. Calvin's hot shit, man. Calvin, dude, that little guy, man, I swear, he's gonna be he's the network prodigal son or something like that. He's the how's this he's the Anakin Skywalker of everything networking. So he's on. So I don't know him personally, but he's obviously he's always on David's Discord. He's on David's Discord. He's on Kevin Baker's Discord. He's making his own YouTube videos now too. A lot about he's on his studies. Obviously, his studies are what are he's what is he? Is he already CCIE certified? I think he is. Yeah, nothing against Network Chuck, but I don't tend to watch Network Chuck's videos, and that's nothing against. I don't know. I can't get into the, yeah. That's a story for another day. He has the CCNP. Yeah, he's a whiz, man. That kid, I tell you, for being 16 years old, holy guacamole, holy guacamole. Yeah. It's funny when the dude started doing Twitch, what was it, about a month ago? Like I was jumping on his Twitch and like trying to be like supportive of him and stuff like that. And it's not like he doesn't know me from, nobody has to, but it's the fact that he was like, I don't know, he was just rubbing me the wrong way. He always just rubs me the wrong way every freaking time, man. And like I was trying to just be, just supportive and trying to just, help with the crowd that on his Twitch channel and stuff like that. Like people were just tossing crazy links in his Twitch channel and stuff like that. And I was just trying to tell people like, that's not what you should be doing. And I was just trying to notify Chuck, like, Chuck, you might want to monitor this stuff just in case somebody throws a harmful link in your chat. You don't want somebody clicking on a harmful link in your chat and stuff like that. And then he just dogged me for freaking bringing that up. I'm like, whatever, dude. You don't want me trying to help you? I'm out. Peace. And that was the last time I watched him on Twitch. But, yeah, man. Again, that's another story for another day. Yeah. Yeah, exactly. I'll stop there then. Yeah. All right. What can we lab now? What should we lab now, guys? What should we lab it up? Yeah. That's gonna take me a bit. You know what? Oh, man. You know what? You got me now thinking like, how am I gonna get this? How to get that? I might actually ask Calvin. I'll probably jump on David's Discord and maybe just drop Calvin a line real quick, because I believe that's what he uses to do a lot of his IPsec training and whatnot. He uses. I mean, there's got to be a way to get this stinking cloud service router working. You know what? Let's do this. What other labs do I have right now? Do I have? I have an internet connection on this one. Right. So I already got. I got this working already. So just this was, you know me and my love for DHCP. So this is just a topology that but I'm thinking if I toss the cloud service router in here. So this is it's a NAT bridge. So this is performing that. This router is performing that too as well. And then I have I configured, because what I did was I configured the Ubuntu server image. I downloaded the DHCP software to it, and that's actually that's performing DHCP for all of these over here. But what I'm thinking though, LMAT, is so I don't have to get into all that other configurations. If I drop it in here, because I already got everything working in this topology. Let me just condense the topologies. Yeah, that's what I'm thinking. And you know what to do? I'll hook it up to this server switch right here. No, not that one. Let's hook it up to this one. That way I could get it off of one of these guys over here. All right, create the link. I don't even have to waste my time with these guys. All right, let's do it. Let's see if we can get it up and running, because you got me thinking now. If I can get it to work this way, I should be able to get it. Yeah, that should work, because it doesn't even matter that it's sitting on another VLAN. It won't even care. Yeah. Yeah. And then I should be able to, yeah. Yeah. I think this, if anything, this would be like the quick and fast way to see if we can get it. Yeah. If I continue to run into issues with it, I will. Most definitely we will. Come on, baby. Come on, router. Do some routing. Do some routing. Let me get this part up too at the same time. Oh, so this is just off my yeah. I'm just using all off actually one PC. Here. This is my PC. If you this is my whole setup, man. If you're just curious. So there you go. You can take a look at um that's what I'm running right there. Um LMAth. Uh that's it. It's all running off. So my stream, my server, everything I do is just off of this. Dude, I run this all off of Ryzen 5 1600 CPU. Surprisingly enough, man, I tell you that little Ryzen CPU, man, that thing is the workhorse of workhorse CPUs. I'm telling you, it is worth every penny, and it's actually pretty cheap too. I got mine. Um, yeah, that's what I didn't think it was going to be able to handle all of this all at the same time, especially doing the stream and everything else all at the same time. I did not think that first off it could handle because I'm running VMware Workstation Pro on top. That's what's running my EXXI server, and then obviously EXXI. That's where I run all my VMs, and that's where I'm running CML right now is inside of VMware ESXi. Um, oh yeah, I mean the next ADubs, the next step is I'm shooting high. I'm gonna be going for the Threadripper. I want 32 cores. Um, because I've already ran into I can right now with streaming and doing all of this, um, with streaming and doing all of this, I already ran into the issues where I peaked out at running. It was like I think it was like 5 or 6 VMs, and then I started having issues. Um, so I mean, 32 cores should be well and enough. Yeah, yeah. Oh, I mean, dude, AMD Ryzen's I mean, their stuff's awesome, dude. Awesome stuff, dude. I mean, exactly like you said, the Zen 2, yeah. I mean, anything. Um, but bec- the thing is, like, I'm like, I know I want to make a dedicated. I want to make a dedicated server because so what I want to do next is um I want I want to get I want to get by Intel. No. um my next step and the reason why I kind of want to make a dedicated I want a dedicated just system just for this stuff is I want to get vCenter up and running. I mean, I can get vCenter up and running now, but I might be it would be it wouldn't make a like if I would getting vCenter up right now, it just wouldn't be logically like why would I get vCenter up if I'm running it off of all the same um, quote unquote server, you know what I'm saying? So I want to actually break off a dedicated um, uh, I want to like dedicate an actual server so that way I can start doing because what I want to do with vCenter is I want to stop messing with vMotion and moving things left and right from server to server without no interruptions. That's because that's going to be part of my studies for my VMware certification. There is learning how to use vMotion and bouncing VMs back and forth to server. You know what I'm saying? And creating high availability areas and stuff like that because what I want to demonstrate because my sister works in the IT field and her boss once told me I didn't know what I was talking about with EXXI. Well, the thing was is he doesn't even know how to use Proxmox, okay? And he owns a software company, and I was like, dude, like, because they do this thing called upgrade night where they have to take down all their servers and they have to shut everything down, upgrade everything, then bring everything back up. Um,
Pretty sure my laptop can't handle versus dude. Get on your VM train.
I do. Let me see. I mean, I built this whole. I think that all in all, that cost of building this whole thing, I think it was only like $900. It wasn't too bad. I mean, I did it all last year. Um, Woo! Look at my usages. All right, let's power this up and hopefully this doesn't fry everything. Let me just make sure I can ping Google. Yeah, exactly. Fingers are crossed. Exactly. Yep. Getting 1,000 trace backs. That's the thing with these iOS Vs. I don't see. I think you gotta like when you do NAT on these iOS Vs. I think you gotta increase the the use the usage is on it. Like give it a little bit more RAM or CPUs because dude, I'd be getting when every time I configure NAT on these iOS V images, like I get these crazy tracebacks. Like they won't stop either. I don't care. Whatever. Trace back it up. Whoa! 74%. Yeah. Oh, it won't stop either, trust me. Let's just make sure I can ping Google. Alright. I just wanted to make sure we can ping Google. That way. Holy some mulligans. I'm gonna blow up my computer tonight. Trust but verify. I'll donate $5 if you prick it. Thank you, man. That'll buy me the tissue. So after when I cry, after I brick my computer, that'll just buy me the tissues. Oh shit! I tell you, man, I've tortured this computer, man. I'm like exactly. I've blue screened this thing so many times since I've made it. I've tortured the crap out of it. Like when I first was learning how to virtualize it, um, I don't know what I did wrong, but I did something wrong. Um, I messed up one of the settings in the BIOS one time, and yeah, it took me like a day and a half just to get the thing to boot back up again. Uh, it was amazing. All right. Oh, let's keep our fingers crossed on this one. Give me a console. You share how you get yeah. Yeah, so I'm running EXXI right here. So I have I got VMware Workstation Pro running EXXI. And that's it. Even though it's a bare metal image, um, you can just boot it right off of VMware Workstation. Um, that's it. Do you need Pro? That's a good question. I don't think you do. Honestly, you could probably. I I believe. Um, I believe you can use the. I believe you can use the whatever the they have like those the because VMware they have those two yeah. If you have any questions, just come back. I'll be streaming again tomorrow. Um I don't know if you can do it off you might be able to do it off the player. Um but I want to say VMware has like those like free instances where you get to like run it for like 30 days or 90 days. Um it should you can I believe there's even one like a ESXi too that uh, you can download for free too and use that image for about 30 days too, um, just to for testing purposes and student purposes. Oh, did you? Hmm. I mean, honestly, man. I mean, if you're, I mean, again, um, I went, just because. Yeah, you can get EXSI on a Raspberry Pi, most definitely. Again, you know, ooh, we might be booting up, guys. For me to boot, I mean, to boot up EXSI on a Raspberry Pi is great to say you can do it. But the thing is you got to have to load that up, though, that Pi with extra resources just to really do anything with it. You know what I'm saying? Um, that's the only caveat to booting up EXSI on a Raspberry Pi. Um, Whoa! What happened? Um, you know, again, to do it is great. You know what I'm saying? And I wouldn't tell I would tell anybody, yeah, go ahead, do it. But again, you're gonna have to give it additional resources, um, to just be able to do anything you want with it. You know what I'm saying? Because again, ESXi is it's a layer one hypervisor. So pretty much you're wiping your operating system, and that's just going to be the actual operating system. AXSI is it's like Windows or anything else. It's an actual operating system, uh, but you have the ability. You can virtualize anything on EXXI after that. Uh, I love EXXI. I think it's great. You know what I'm saying? I still want to get. I'm gonna eventually when I have some more resources, I'm gonna start dabbling with Proxmox just to get my handle on Proxmox and stuff like that. What's going on? Looks like come keep alive. command on this thing? Whoa, 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 whoa. Oh my goodness, stop it. Did you get an address at least? I might call it here myself soon. It's too much to troubleshoot live. Yeah. It might be, dude. Dude, I appreciate, yeah. Yeah, this is gonna be an adventure probably that I'll have to do on. That's probably gonna take me some time, guys, to figure out how to. Like I said, I will definitely figure out how to get this up and running for us guys. I will definitely figure out how to get this up and running for us. But yeah, I appreciate you all joining me. I got something special. I got something special for tomorrow, guys. I'll probably be streaming a little bit earlier tomorrow. I got something special planned for us that's going to be an addition. It's going to add just a little bit to the stream. But tomorrow we're going to be picking up. Remember, we just completed part 4, so we're going to be picking up on part 5. All right. Yeah. We're going to be picking up on part 5, and that gets into actual routing. And again, we know a lot about routing already. Yeah, man, no problem. Dude, thank you for stopping by, Hellmouth. I appreciate that. And same to you, A-Dubs. Dude, A-Dubs, you're awesome, man. I appreciate you sticking around too, A-Dubs. A-Dubs and Hellmouth, dude, you guys are awesome, man. Appreciate you guys just conversing with me and hanging out, you know. Because that's what it's about, man. I love this stuff, dude. I love, yeah. We're all gonna be network engineers, man. But if I have anything to do with it, we're all gonna be network engineers, dude. All right. All right, A-Dubs and Matt, you guys have a good night. Like I said, same time tomorrow, 5 o'clock Eastern Standard Time. I might be on a little bit earlier. And like I said, I got a little surprise for everybody. I just got to get it set up tonight. And we're going to go from there, guys. All right? You guys are awesome. All right? I appreciate you guys. And you guys have a good night. Good night. Let me see. Let me get you my other screen. It's gonna be a good night. Get my little fireworks. Pew 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 pew. Go to see a good night. I'm gonna shut this CSR down before it blows up my computer. Stop, lab. Stop it. Let me play some of my groovy music real quick. All right, everybody. Like I said, I'll see you all again tomorrow, 5 o'clock Eastern Standard Time. I'm gonna get into part 5 now, which is IP routing. But you guys have a great night, and I appreciate you all joining me. Everybody, have a good night.